हेलो। हेलो।
അല്ല
എനിക്കൊന്നും കേൾക്കാൻ പറ്റണല്ലോ.
ഇത് ഓക്കെ ആക്കിക്ക്
ഏ?
മാക്സിമൈസ് ചെയ്തേ കേൾക്കാൻ പറ്റുന്നില്ല. മുകളിലേക്ക് നോക്കി അവിടെ നോക്ക്. ആ ഓക്കെ എന്നോട് പറഞ്ഞു. ഓക്കെ
हेलो। Am I audible?
Hello.
Hello, am I audible?
Yes, yes.
Okay.
Hello, ma'am. Can I share the screen? It's disabled.
Just wait a minute. Good afternoon, all. Welcome to second day of STAM 2023 International Conference conducted by Mathanasius College, Kodamagalam. This is the second session of online oral presentation. The judges for evaluation are Professor Dr. Thomas Verghese from Nirmala College, Muattabura, and Professor Dr. Franklin J. from SH College, Tevara. On behalf of STAM 2023, we welcome both of you. Presenters, please note, the rules of presentation is time of the presentation is 8 minutes and time for the Q&A section is 2 minutes. Presenters, please note the time carefully. Let's start with the first presenter. ID number 082, Neena P, SNM College, Maliangara. The topic of presentation is development of nanocomposite with LDPE and graphene nanoparticles by means of melt extrusion method.
Ma'am, please allow me to share my screen. Hello, am I audible? Hello.
Yeah, you can share your screen now.
Okay. Is it visible? Hello?
Yes, we see.
Can I start the presentation?
Okay, you can start.
Good afternoon all. Today my topic of discussion is development of nanocomposite with the LDP and graphene nanoparticles by means of melt extrusion method. The matrix material which we used for the study is low density polyethylene. As you all know, HDP and LDP are the most common polyethylene materials which are used widely. I selected this material because it's a soft, flexible and lightweight plastic material. And also it have good corrosion resistance. And the filler material which we used is graphene nanoparticles. It is locally purchased. And these two, the filler and the composite material is mixed with the melt extrusion method. We pelletized a sample at 448 Kelvin. And the samples were prepared using ASTM standards. By varying the amount of graphene nanoparticles from 2 weight percentage to 10 weight percentage, we had prepared 5 samples and we compare it with the pure LDP sample also. The characterization techniques which we are used is UV visible spectroscopy and differential scanning calorimetry. First, we will discuss about the UV visible spectroscopy. From figure itself, you can see that this is a virgin one, black one. Virgin material does not have any absorption, and it is seen that as the amount of filler material is increased, the absorption is found to be increasing. This is due to the great surface area, larger delocalized pi electrons, etc. And it is also seen that the 230 nanometer characterization peak is also seen here. That peak is due to the pi star plasma value. Now we are going to the differential scanning calorimetry study. And in this case, we have used the 5 samples and the virgin material. You can see that this is the glass transition temperature happens here. And the peak value of virgin LDP is shown at 324.7. We can round it as 325 Kelvin. And due to the this glass transition happens due to the partially ordered interface between the lamella and the amorphous region, and it is also known as glass transition or alpha transition of LDPE. And here, with the increase of graphene, that is a filler material, it is found that LDP matrix shows variation, glass transition temperature variation towards a high value. That is, here it is noted as 327.5 Kelvin, and this indicates the effect of nanoparticles in the mobility of the molecules in the matrix. These graphene particles have some effect in the mobility of particles. Now we are going to the melting behavior. This peak shows the melting behavior. And in this thermogram is used to determine a number of parameters here, that is onset of temperature, peak temperature, and heat of fusion. So melting temperature of crystalline polymers normally depends on the size and perfection of their crystal units. Here the melting temperature of LDP depends on the filler particles of the composite. The virgin LDP shows the melting temperature at 389.42. You can see it here. The peak melting temperature of LDP composite is shown to be slightly increasing with the increase of the filler. This is probably due to the fact that graphene nanoparticles absorb more heat during the melting of composites. The melting endotherm also starts at lower temperature in these composites than the virgin LDP. This is due to the larger crystalline size and narrower size distribution of LDP in the composite. So these features indicates the improved thermal stability of the composite. And it is also observed that the delta H fusion value, it is also found to be increased with the amount of filler particle. Now we are coming to the crystallization behavior of the material. The DSE thermogram of virgin LDP and its composites in the region of crystallization is recorded during the cooling scan. The crystallization behavior is over from the temperature range 398 Kelvin to 363 Kelvin. The increasing concentration of graphene nanoparticle in the LDP matrix resulted in the decrease of TCO, that is the onset temperature of crystallization is found to be decreasing. The decreasing TCO clearly indicates the delay in nucleation. Nucleation means the ability to crystallize from the liquid phase. In the onset temperature usually indicates the beginning of crystallization process. And the maximum of exothermic peak indicate the occurrence of spherulite impingement. The increase of peak crystallization temperature of the LDP with the increasing concentration of graphene powder suggested that the crystal growth of LDPE in the composite would take place at higher temperature, leading to larger crystalline size and improved crystal perfection and narrower crystal size distribution. And in this graph, you can also see that as the amount of graphene percentage is increasing, the crystallinity of the material is found to be increasing. To conclude, a series of LDP graphene nanoparticle composites have been prepared and extensively studied for the optical and thermal behavior. The LDP with graphene composite exhibited higher thermal stability than neat polymer. And this work clearly shows graphene powder can be effectively used as reinforcing material in thermoplastic LDP matrices. It's a good alternative, commonly used LDP composites with the inorganic and organic fillers. Since nanocomposites are scope for the future and considered as a material for next generation, there is an imminent requirement to investigate the durability of this nanocomposite in different environmental conditions and to extend its applicability in various versatile fields. Thank you.
Audience can ask questions.
Pardon, sir? Not audible.
Audience, you can ask questions.
Okay.
Any questions from the audience side? Okay, can I ask one question?
Yes, sir.
Okay. What is the final outcome of your work?
Pardon, sir. What is the
Final outcome.
final outcome?
That
Okay.
means
Okay. Okay.
where
You
you can apply this material.
can,
What is
so,
the potential use of your material?
this material can be, while adding graphene, we can improve the conductivity of the material so that we can use this material in different applications, electromagnetic shielding like that, and in biomedical materials, in sensors, etc. A membrane type of this material can be used in a variety of applications.
But you have not done any application work, right?
No, sir.
Okay, then what about your extrusion method? You didn't mention anything about that method.
Pardon, sir?
Melt extrusion method.
Melt extrusion method.
Yeah.
Melt extrusion method means we are heating the material up to its melting temperature so that we can mix the matrix and the filler without any solvent.
Okay. Okay, but you didn't include any slide on the
Okay, sir.
timing, sir.
I do have some doubt about differential scanning colorimetric graph which you have shown. So you have observed that when you are when there is an increment in graphene percentage, you said something like delaying nucleation occurs.
Yes, sir.
Why is it so?
Because this graphene nanoparticles absorb a lot of heat.
And how is it connected with the crystallization behavior?
Crystallization behavior we are studying in the cooling phase.
Could you please show me that slide once again? Actually, I missed. Okay, just okay. Crystallization behavior increases. Okay. Could you please also show the DSC graph just before this? Okay. 360 degree. Okay, your crystallinity also is increasing. It's both are showing the same trend, right?
Yes, sir.
Okay, what is your? Yeah, I'm your final conclusion is not quite understood by me. So in connection with the same question, Dr. Thomas.
Okay. By this study, what I mean is with the addition of this graphene particle, the thermal stability of the material is found to be increased and the quality of crystal is found to be increased.
Okay, thank you.
Okay, sir. Thank you.
Any more questions? Okay, thank you.
Thank you, Neena. Now
Okay.
let's move to the next contestant. ID number 083, Krishna Kumar Meletil from Newman College, Todupuzha, presenting on the topic, a fully sustainable approach for the preparation of imogolite NTs, electrosensing of p-nitrophenol over silver La-IMO NTs.
Good morning, ma'am. Good morning, all professors and judges. Can I start?
Yeah, you can start.
Thank you, sir. My slides are viewable.
Okay, it's okay.
Yes, yes.
Oh, okay, sir. Thank you. 1 minute. Mm. Okay, today I'm talking about a fully sustainable approach for the preparation of immaculate nanotubes. And it's applied as, it's just showing as an electrosensor for paranitrophenol uh, phenol using by loading silver on immaculate nanotubes. In this discussion, we going through these parts: introduction, experimental section, result and discussion, and conclusion and references, question and answers. So introduction: what are immoglates? Immoglates are actually naturally occurring aluminosilicate based single walled nanotubular clay minerals. It's obtained or found in uh, soil nearer to volcano. So it's found in volcanic ash because it needs more alumina and silica content. It's actually formed by the combination of alumina and silica. So its general stoichiometry, we can simply say that outer surface is made by alumina particle, and inner tubular wall is made by silica. And it's,
Excuse me.
yes,
Are you
yes,
moving ahead with the slides? We,
yes,
okay, now only the corresponding
yes,
slides.
sir. I think some problems, so I will show like this.
Yeah.
And in this thing, one more thing, it have more advantages. It's inner and outer surface containing uh, OH groups, so it can carry many kind of materials, metals, and many kind of biological molecule also. So it is used as DNA carrier also. So it is a material which very much potential applications. So in this work, generally in past works, mainly they extracted or taken from these volcanic ashes. But here we try to prepare in our lab conditions. In lab condition, most of them are prepared from TEOS as silica source, but here we used as RHA, rice husk hash as silica source. After the burning of rice husk hash at higher temperature, we dissolve that rice husk hash into 3 molar sodium hydroxide, and we convert it to sodium silicate. And here sodium silicate is the silica source, and we applied fatty acid, a naturally occurring fatty acid, lauric acid, as um, template how it's act or how it's help uh, to form immolate nanotubes within few days. Actually, it's a time taken process, 3 to 10 days. Here we only treated 4 days. So the other thing is, we load silver nanoparticle on this immolate nanotubes for it makes conducting. Actually, it's an insulator material, and we used it as a nitrophenol sensor. So when we go to experimental section, we just taken everything in millimolar concentration. So into lauric acid solution, we add aluminum nitride in millimolar concentration. After treating it in 80 degrees Celsius, we add sodium silicate. So after adding the sodium silicate, we slowly set its pH to um, pH to circumneutral pH, that means 7, using low molar sodium silicate. Um, After that, at 90 degrees Celsius, we treat it in hydrothermal treatment. That means we treat it in autoclave for 4 days. After that, we purifying this material. We load it by adding we load silver to immolate. using AgNO3 as a silver source and by the use of ascorbic acid as reducing agent. And this material we coated on carbon paste electrode, and then we used it for electrosensing studies using for nitrophenol. And we can go to the resultant discussion. In this characterization techniques, we used first as FTIR. In FTIR, we just proven that it's a hybrid material. It's a combination of lauric acid and immoglate nanotubes. In the preparation of blank sample, we don't use lauric acid, so it forms an actually combination of allophane and gibbsite. That means it's only containing aluminate and silica. There is no formation of immoglate nanotubes, so the peaks also have very poor, and there is no organic peaks. There is no lauric acid peaks because it's not containing lauric acid. But in the case of other two samples, this is lauric acid containing immoglate nanotubes. So here we can observe the lauric acid peaks, as well as we can observe two major peaks obtained in immoglate. This is SiO-Si peaks and SiO-Al peaks. So we can say that the hybrid material is formed at the same time. We can obtain some immoglate peaks. And after that, we do TGA. According to TGA results, we can say that when the material heats at inert condition, the lauric acid decomposes from 300 to 400, and its weight losses up to 50 percentage. And the interesting thing is, when we compare with the 3 weight percentage AgIMO-NTs and LaIMO-NTs, the weight loss is 3 percentage. The final weight percentage weight loss is 3 percentage. So we can tell that 3 percentage Ag loading is successful. And finally, we are going to XRD. According to XRD results, in blank IMO-NTs without lauric acid functionalization, it forms gibbsite or bombate. Gibbsite also a variant of bombate. So it forms gibbsite and bombate. And we can observe some unreactant silica also in all the samples. That's the reason for this amorphous peak, starts from 20 to ends into 30. And but in the case of lauric acid loaded samples, we get many peaks of immoglate. This is the 110 plane of immoglate, and 001 and 211 peaks of immoglate. And we can observe a peak at 3. That's the 100 plane of immoglate. It's here. Actually, when we draw with more resolution, we can observe that peak. This is a major peak of immoglate, and it passing through the center of the immoglate nanotubes. So it's 100 plane. This is the explanation of immoglate XRD peaks of immoglate nanotubes. And in the interesting thing is, we can observe the silver phase outing at 5 weight percentage AgLi-IMO-NTs. That is also underlined by the TEM images. Here we can see that in the case of blank IMO-NTs, there are some circular shaped formation of aluminate and silicon nanoparticle. But in the case of lauric acid functionalized immoglate, we can show the formation of some tubes on lauric acid bed. Actually, lauric acid formed as a layer, and on that layer we can observe some tubes. In the case of silver loading, 5-8% silver loading, we can observe some silver particle nanodots at 8 nm. And it also show in SCED pattern also. And finally, we are going to the electrosensing part. In electrosensing part, we can say that LAIMO actually it's performing as an insulator, but by Ag silver Ag nanoparticle loading, it becomes conductive. So we can say that our work is successful, and we can just show that electrosensing is possible by loading a few amount of silver on immobilized nanotubes. And this is the electrochemical cyclic voltammetric profiles. According to these profiles, we can show a reduction peak of 0.8 volt minus 0.8 volt. It's a characteristic peak of reduction of nitrophenolate ion from nitrophenolate ion to para-hydroxyl aminophenol. And this para-nitroso-aminophenol again oxidized to para-nitrophenol. That peak is here. It's not clear actually because the graphs are small. That's why happening here. And at this reduction and oxidation, here silver also happens some oxidations. In the case of silver, it cases two kind of oxidation. Firstly, it oxidates to Ag plus at 0.3 volt, and it again oxidates to Ag2 plus. It's happened here. We can observe some two twin peaks. Silver loading is very less in these samples, so that's I thought the peak is very small. It's Ag plus formation, then Ag2 plus formation also happen here. This oxidation also reduces nitrophenol, and that leads to the reduction of nitrophenolate ion, and electrosensing is possible by loading silver on immobilized nanotubes. That's I observed. And finally, we are going to conclude. According to our results, we convert a waste biomass, that means rice husk, to sodium silicate as a good reactant. And here we can say that lauric acid templation is also a good thing. So functionalization through lauric acid leads to the formation of immobilized entities within few days. And the silver loading also make it as a conductor from insulator. And millimolar sensing of nitrophenol is also achieved. So the work is success, and this is our conclusion. And these are my references, and we can go to question and answers. Thank you. Thank you.
Ranjan sir, have you any questions?
Yes, you are talking about the applications of these IMO nanotubes as DNA carriers. How is it?
Yes, sir.
Is there any references regarding that, or how
Yes,
is it?
sir. Sure, sir. Sir, it have a paper, it's published on RSC. They say that immobilized nanotubes have some interaction with a phosphate group of DNA. So they, in that work, they used it as messenger RNA. If you are interested, I will forward, sir, definitely.
What is it? Is the
Sir?
outside the surface?
Sir, it's not audible actually. Can you ask again? Hello.
Can you hear me now?
Yeah, now I am audible, sir.
Okay. So DNA is polyanionic, and how much is the charge density as per your understanding about the charge density of these nanotubes?
Immogolite. In that paper, actually, they are not talking about charge density. They are mainly talking about the surface area and the presence of aluminol groups. That means OH groups on the surface of the immogolite outer surface. They telling that these OH groups interact with the phosphate groups present on the DNA, and they can carry DNA. They can these immogolite nanotubes can carry DNA.
And what is your next direction in which you will be proceeding? What's the future?
Sir, in this belong with this work, I do the photochemical reactions also. So it's also successful, and it is actually it's more good for photochemical reactions. That means photo reduction, catalytic reduction. So so I completed that works also. So I am waiting for the publications.
Okay.
Actually, now I am not working on that field.
Okay. Thank you.
Okay.
Can you show the 10 images?
Sure, sir. Sure. Is it visible, sir?
Okay. Have you measured any dimension?
Yes, sir. Actually, it's showing 1 to 2 nm diameter. Actually, it's just the formation. Actually, it's a basic. It's a small formation of immogolite nanotubes we can observe. We cannot tell that it's successfully it forms a tubes because we only treated as 4 days. Actually, it's a time-taking procedure. Actually, these tubes are formed within very. It's a time-taking process. It takes more days.
Because by seeing this figure, we cannot say it is tube-like structure. Then did you measure the aspect ratio?
No, sir, no, because actually TEM images is not
no
clear. I
problem.
think
Then
it's an
what is the confirmation about the SID pattern?
according to SAD pattern, it's a semi-crystalline or it's a in-between stage of amorphous and crystalline nature. So according to this, we can say that it's a in-between stage, and we can observe some silver plane also.
Is it clear? 111 plane?
Yeah, its AGS 1 plane is observable here. Here.
Okay, thank you. Any
Thank
more
you,
questions from audience side?
Thank you, Krishna Kumar. Presenters, please note that the presentation time is 8 minutes and the Q&A time is 2 minutes. Make sure that you finish the presentation within 8 minutes.
Yes, sir. Thank you. Thank you.
The next presenter is Karthik Vinodan from Catholicate College, Pathanamthitta, ID number 084, presenting on the topic Enhanced Energy Storage and Pyroelectric Properties of PVDF TRFE CTFE based nanocomposite films.
Hello, ma'am. Is it audible?
Yeah, it's audible.
Yes.
Okay, you can start.
Is my slide visible?
No, it's not visible.
Okay. Sorry, ma'am. I am looking it. Is it visible, ma'am?
Yeah, the screen is visible now.
Okay. So, good afternoon all. So today I'm going to present the topic enhanced energy storage and pyroelectric properties of PVDF, TRFE, CTFE based on nanocomposite films. Coming to the background behind this work, we know that the demand of energy to power various devices and electronic power systems is rising globally. So to address this energy demand, the challenge is to adopt various approaches to harvest energy. And we know that there are so many materials that respond to different kinds of environmental stimuli like mechanical vibrations, heat, electric field, magnetic field, and in response to that stimuli, they will produce a new electrical output. And these electrical output can be stored or harvested for various applications. And basically the temperature and electric field dependent properties and also the dielectric properties of the materials make them a potential candidate for various energy related applications. And we know that there are a category of materials known as ferroelectric materials. They possess such multifunctional properties and can be devised for various energy harvesting applications. And also we can use ferroelectric polymer ceramic composite technology in which the merits and demerits of each such phase can be tailored and we can tune for designing new systems. And coming to the materials and methods I adopted, I selected the sodium niobate ferroelectric as the filler part due to its high electric permittivity and also low cost, non-toxicity. And mainly it is electric field, it have electric field dependent polarization. And coming to the polymer part, terpolymer, PVDF, TRFE, CTFE is selected as the matrix due to its inherent relaxer behavior. And also they possess the temperature dependent and electric field dependent polarization that can be used for harvesting energy. And the sodium niobate nanoparticles is synthesized using sol gel method, and the composite films are prepared by solvent casting method. And here the pure polymer is abbreviated as PVTC, and with the different loadings of sodium niobate, it is abbreviated as PVTC 5NN, PVTC 10NN, and PVTC 20NN. And coming to the synthesis method, sodium niobate nanoparticles are prepared by sol gel process. Here the stoichiometric coefficients of sodium carbonate and ammonium niobate is selected. And citric acid is used to enhance, and ethylene glycol is used to used as a stabilizing agent. And finally, the final solution is stirred, dried, and calcinated at 700 degrees Celsius to obtain the pure phase. And terpolymer nanocomposite films are prepared by solvent casting method. And for that, the polymer part is fixed and the sodium niobate part is varied. And after complete solution dissolutions, films are casted in a petri dish and it is dried at 60 degrees Celsius. And to improve crystallinity, it is again heated at 100 degrees Celsius for 2 hours. And coming to the results, the XRD results obtained for sodium niobate nanoparticles obtains confirmed its purity, and it was also confirmed by comparing with the JCPDS data. And average crystalline size found to be 28 nanometer. And coming to the XRD data of composite films, we can see that the presence of electroactive phase of the polymer in each composite films, and also the peaks corresponding to the sodium niobate also get enhanced with the loading. And coming to the FTR studies, the FTR studies depicts that the electroactive polar peaks of the composite films get improved. And coming to the morphologic studies, we can see that the majority of the nanoparticle synthesis as spherical, and also the despacing corresponding to the planes 101 and 141 were also marked using HR-term micrograph, and elemental composition were confirmed using EDA spectrum of the sodium niobate nanoparticles. And coming to the morphology of the nanocomposite films prepared, we can see that the morphology of the pure films changed with the filler addition. That is one of the main characterization of solvent casted film. And the electrical study is mainly done using dielectric properties, and dielectric properties of the composite films improved with the filler addition. That is actually one of the main characterization of solvent casting process, and it is mainly due to the interfacial charge polarization between the filler and the polymer part. And coming to our main storage related studies, actually the energy storage related studies were done using ferroelectric P hysteresis loop studies. And from the loop, it is clear that actually the green portion of the graph, which is actually used for recovering energy density, and the pink portion is actually the loss energy density. And for exactly calculating the energy discharge energy density, we have to integrate EDP from the limit P remanence to P maximum. And this is the result that is obtained for the pure polymer and with 10 loadings of sodium niobate and 20 loadings of sodium niobate. And also the energy in another approach, also the energy harvesting studies were done. That is, it is a thermodynamic approach. Here also ferroelectric P hysteresis loops were used to study the pyroelectric energy harvesting property. And here, 2 hysteresis loops are obtained for 2 different temperatures. And here a loop is obtained, and here and the area enclosure the loop is used for calculating the energy harvesting density. And this is the pattern that is obtained for the composite films. So we can see that here also the polarization of the nanocomposite films is changed for different temperature, and this change in polarization is used for calculating the energy harvesting density using pyroelectric method. And this is actually the comparison of the result that is obtained. The discharge energy storage density improved with the filler addition, and also the pyroelectric energy harvesting density also improved with the filler addition. And coming to the conclusion, various polymer nanocomposite films were prepared, and various structural, morphological, ferroelectric, and energy storage using 2 different approaches were carried out. And nanofiller incorporation actually improved the storage properties, and we can tune different polymer and filler part to develop such storage devices for various applications. And this is the references I used, and thank you.
Thank you.
What do you mean by this pyro harvesting property of this?
Okay, sir. Actually, by pyroelectric harvesting, actually we meant to harvest the energy using the low grade heat. From heat, we are harvesting the energy density from that.
Can you say what is the novelty of your work compared to literature work?
Sir, okay. Here actually the polymer that I selected is PVDF, TRFE, CTFE, and it is actually a little bit having a relaxer behavior, and that is doesn't used much in energy harvesting aspect using pyro technology. So that is mainly we used for this polymer having certain novelty for this type of studies.
Then what about the comparison output of your work with others' work comparison?
Comparison. Okay, sir. Actually, here here we did this work at a very low heat and at very low electric field. So due to that, even though our the numerical value that we got is a little bit average compared to others, that can be maybe at future we are planning to improve much further.
Okay. Then what was the particle size of the composite?
Composite or sir, is it the sodium niobate nanoparticle? Yeah. Okay. That actually the crystalline size was found to be 28 nanometer. That we calculated using Scher equation.
28. Okay. Polymer with the filler.
Yes, sir. It was actually calculated for the nanofiller itself for.
Okay. Okay, thank you.
Okay, thank you, sir.
Questions from audience? Okay, let us have next.
Thank you, Karthik.
Okay.
Now let's move on to the next presenter. ID number 085, Bismi Abubakar from Athanasius College of Engineering. Presenting on the topic, effect of curing agents on chloride-induced corrosion. Bismi, please start your presentation.
Hello, is it audible?
Yes.
Is my screen visible?
No, it's not visible.
Okay. Can you see?
Yes, yes.
Good afternoon, everyone. I am here with my topic effect of curing agents on chloride induced corrosion. First of all, introduction. As we all know, corrosion is referred to as the process of deterioration and consequent loss of solid metallic material through chemical or electrochemical attack by its environment. And it requires an anode, cathode, electrolyte, and an electrical connection between the anode and cathode for the transfer of electrons. And the concrete pore water acts as the electrolyte, and the body of the reinforcement provides an electrical connection between the anode and cathode. And this figure shows the reaction that takes place at the anode and cathode. First, at the anode, Fe forms Fe2 plus 2 electrons, and this Fe2 plus pass into the solution, and this free electrons moves into the cathode, and where these free electrons react combines with the oxygen and water from hydroxyl ions. These hydroxyl ions then combines with the ferrous ions to form ferrous hydroxide, which is then converted by further oxidation to rust. The main objective of this study is to find the effect of curing compounds and integral waterproofing compounds and corrosion properties of
Are moving
Can
the
you show
slides now?
the respective slides?
Yes, sir.
We can see the introduction slide only now. The title slide only is visible now. Yes, now it's slide number 6.
Okay.
Yes, it's moving now.
Okay.
Okay. Next is methodology. These are the methods that I follow. First one is the literature review, then the characterization of material, then the mixed design of mortar, the 1:3, and the durability and corrosion monitoring techniques, and final the analysis of result. These are the materials that are mainly used in the study, that is cement, fine aggregate, external curing compounds, superplasticer, cornplast, WL, and crystalline waterproofing admixture. External curing compounds are applied to the concrete surface to retain the moisture and promote the proper hydration during the curing process. And this is applied as a thin film on the concrete surface to slow down the evaporation of moisture from the concrete, as shown in the figure. And in this study, mainly two types of external curing compounds are used, that is water-based and acrylic emulsion based. And the next one used is integral waterproofing admixture, and it is makes it, and this addition of integral waterproofing admixture makes the concrete more resistant to water penetration, and these are added directly to the concrete mix, and this works by filling the capillary pores and micro cracks in the concrete. And mainly two types are used in the study, that is crystalline and cornplast WL. These are the mix design. In this mainly these are the mixes that I have prepared. First one is M0 is the controlled mix. Then CN100 is cornplast. CN100, CN200, CN200 are different percentages of cornplast, and CWP is the crystalline waterproofing admixture that are used in 3 percentages. These are the durability tests that are conducted. First one is water permeability. This is conducted to determine the rate of water flow through the material. Then water sorbidity, this is to determine the measurement of water absorption rate, and water absorption is done to find out the water absorption values of different mixes. And the last one is RCPT. This is the permeability of the specimen to chloride ion can be evaluated. Corrosion test. This is half cell potential is the corrosion test that I am conducting. That is, it helps it measures the electrical potential difference between the surface of the concrete and the reference electrode, and it helps to find out the probability of corrosion tendency and is used to detect the areas of specimen at the risk of corrosion. And a lollipop specimen is casted to test the corrosion. This is how the specimen is prepared. First one, a long steel bar is cut, then heat shrink tube is applied at the end of the steel bar, then it is placed in the plastic mold, and then the mortar is placed. Then after 24 hours, then it is epoxy is applied at the top and bottom of the specimen. Then and after drying, the specimen is ready for the curing and testing. These are the results of compression test. First, from that, these inferences are being obtained. The 7-day strength of the 7-day strength is higher for the specimen with external curing compound than the control specimen, and but the 28-day strength is more for water cured control specimen than external curing compound because of the inhibition of the cement hydration reaction within the concrete, and the rate of gain of compressive strength reduces substantially for external curing compound due to the unavailability of sufficient water in the pores to maintain the rate of reaction. And also and for integral curing compound, the 7-day and 28-day strength is more than control specimen, and this is because of the improved microstructure and reduced porosity. And among integral curing compounds, CN200 and CWP 2% are the optimum percentage and has the highest compressive strength. And comparing the external and integral curing compounds, ICC has higher value of higher compressive strength than ECC and control specimen. These are the result of water absorption. From this, control specimen shows lower value than the specimen with the external curing compound because the water cured, well cured specimen allows more hydration of cementitious material, and AE shows lower value than water-based curing compound because AE forms a thicker and more impermeable film on the surface of the mortar. These are the result of sorbtivity. Curing compounds show higher rate of water absorption than the control specimen. The higher value of the water sorbtivity indicates deeper penetration of water into the mortar and thus an inferior performance. This is because of the fact that the value of sorbtivity decreases with the increasing porosity. And the last one is half cell potential, the result of half cell potential. The graph shows the initial values of the wet and dry cycle that I have done. This is an ongoing project, so the final values are yet to get. So the initial readings are within the range, range with below minus 200. That is that means that the corrosion is absent. So coming to the conclusion, from the obtained result that integral curing compound has a higher compressive strength than the control and external curing compound. The control specimen has lower water absorption than external curing compound, making it more durable and reduce permeability. And control specimen have lower water absorption than the integral curing compounds, and the values obtained after initial wet and dry cycle shows that the specimens are in the specimen the corrosions are absent. These are the references. Thank you.
Prime Minister, any question?
Could you please show the introduction slides again? I missed it.
Okay.
Actually, it was not moving at that time. Okay, the third. Yeah, this slide. Okay, what is the main finding of your study?
Actually, this is an ongoing project, so I have not. I didn't get a final conclusion, so this is ongoing. So what I got, I presented. So some ongoing project.
Okay, thank
Okay,
you.
work is going on. Okay.
Yes, yes.
Okay, thank you.
Okay, thank you.
Let us go for the next.
Thank you, Bismi. The next presenter, ID number 086, Ria Sebastian from Newman College, Thodupuzha, presenting on the topic, the thermal nonlinearity study in anatase, brookite, and rutile phases of titanium oxide.
Hi, madam. Am I audible?
Yes.
Is the slide visible?
Yes, it is audible and visible.
Okay, thank you, sir. Let me start.
It is audible and visible.
Okay, sir. Okay. Good afternoon, one and all. I'm Ria Sebastian. I'm a guest lecturer in the Department of Physics, Newman College, Thodupuzha. Today, I'm going to present the topic, the thermal nonlinearity study in anatase, brookite, and rutile phases of TaO2. First, move to a small introduction. As we all know, the nonlinear property of any material can be tuned by tuning the various properties like crystallographic phase, morphology, linear absorption, particle size, etc. A nanoparticle is a particle having size in between 1 and 100 nanometer. And when we reduce the size of a particle to this nanometer range, we can tune several properties of the materials, especially the nonlinear properties. Move to the instrumentation. In the present work, the Z-scan study is used for do the nonlinear characterization of the material. For that, a blue diode laser was used. The laser beam is allowed to fall on the sample, and the sample scan from -Z through the focus to the +Z distance. And the beam coming out of the sample is split by using a beam splitter into two. And in the present study, only the closed aperture Z-scan characterization is carried out. And for that, before falling to the detector, the sample is allowed, the rays from the sample is allowed to pass through an aperture. The different constant components and their specifications are listed inside the table. The experimental setup that we have in our lab is shown here, and the beam characteristics are 405 nanometer diode laser, blue laser is used for this purpose with a beam spot size 14 micrometer, and power of the beam used is 80 milliwatt. To do the standardization of the sample, I took the curcumin dye for this purpose. For that, I mixed 1 ml curcumin powder in 5 ml, sorry, 1 mg curcumin powder in 5 ml water. And then the characterization is carried out by using this diode laser. And I got a transmittance versus Z plot of the closed aperture Z-scan like this. There is a peak which is followed by a value which is a clear indication of the negative nonlinear refractive index of the material. And I got a value of N2 in the order of 10 raised to -11 meter square per watt, which is in good agreement with the literature values. Move to the result and discussion. Here I took the TaO2 for the study. TaO2 has eminent features, good features and applications in variety of fields, including photovoltaics, photocatalytic, nonlinear optical devices, etc. It possesses three different crystal phases, anatase, brookite, and rutile. Usually, it shows an amorphous nature at the room temperature. And when we anneal the sample, we got the anatase, brookite, and rutile phases. And annealing above 600 degrees Celsius at high temperature, that will give the pure and stable rutile phase of TaO2. In order to prepare the TaO2 nanoparticle, a sol gel method was used with TTIP as the precursor, and different concentrations of oxalic acid is also incorporated into the precursor to prepare the TaO2 sample. To prepare the nanofluid for the Z-scan study, I mix 1 mg of nanoparticle in 10 ml water when it is ultrasonicated for 30 minutes. So the different samples that I have in this study, 12 different samples in 4 different categories, 4 different temperatures. One is as prepared temperature or room temperature. And then the samples with 400, 600 and 800 degree annealing temperatures. And in each annealing temperature, there are 3 different samples without oxalic acid with 25 and 50 ml oxalic acid samples. The morphological characterization is carried out by using the FESM analysis, and the morphology is an agglomerated spherical-like morphology for all the samples. And the different average particle sizes of the different samples are listed inside the table, and it can be seen from the table that as the annealing temperature increases, the average particle size increases, And at a particular annealing temperature, with the amount of oxalic acid enhancement, an enhancement can be observed in the particle size also. Then X-ray diffraction characterizations were carried out, and the XRD pattern of the sample at a room temperature is here. S1, S2, S3 samples. Clear, sharp crystalline peaks are not visible, so I considered it as amorphous. And when it is annealed to 400 degrees Celsius, three different samples are here with a 25, 50, and 0 ml oxalic acid. And as the amount of oxalic acid increases, the rutile phase of TaO2 begin to emerge. In the case of 600 degrees Celsius samples, for the first sample, S7 sample, there is a peak corresponding to anatase. But from there onwards, from S8 onwards, only the rutile phase of TaO2 is visible there. In the case of 800 degrees Celsius sample, irrespective of the amount of oxalic acid, all peaks are corresponding to the rutile phase of TaO2. Then average crystallite size is calculated from the Sher equation, and it is listed inside the table. And as the annealing temperature increases, an enhancement can be observed in crystallite size. Then in order to find out the different phases, the percentages of anatase, brucate, and rutile phase of TaO2 in each sample, I deconvoluted the XRDs, and the different weight percentages are listed inside the table, and it is visible from the table that as the amount of oxalic acid increases, in all cases, an enhancement can be observed in case of in the amount of rutile phase of TaO2. But in the case of final samples, that means from S8 onwards, irrespective of the amount of oxalic acid, only rutile phase are there, because this high temperature give only the stable rutile phase of TaO2. And then the reflectance spectra, UV reflectance spectra of different samples are here. The third sample, C1, the sample C, it is visible that as the amount of rutile phase of TaO2 increases, spread can be observed more into the visible region compared to other samples. Then the nonlinear characterizations were carried out by the Z scan technique, and the Z scan, the peak, then the variation of normalized transmittance versus Z peaks are here for all the samples. In all cases, a negative nonlinearity is visible because there is a peak which is followed by valley in all cases. How the linear variation, the alpha, linear absorption coefficient, how it varies with annealing temperature, which is plotted here. As the annealing temperature increases, an enhancement can be observed in the case of alpha, because of this, there is an enhancement in particle size which helps to increase the value of alpha. And in the case of when we plot alpha against amount of oxalic acid for each annealing temperatures, the maximum, there is a change in all cases, but the maximum change can be observed in B and C, because in B and C there is a transformation from other phases to the rutile phase of TaO2. It is visible from B and C compared to A and D. But in A and D there is also an enhancement that is mainly due to the increase in particle size due to the agglomeration which occurred by the presence of oxalic acid here. Then the variation of N2 with the annealing temperatures are here. In all the samples with a different amount of oxalic acid, in all the samples, N2 enhancement can be observed with the temperature. It's mainly because an enhancement in alpha is here. Alpha has a direct effect on N2 in case of thermal nonlinearity. That effect here. And in the case of when we plot the amount of oxalic acid versus N2 in different annealing temperatures, from this graph and also from this bar diagram, it is visible. In the bar diagram, second diagram, the maximum change in rutile phase is observed in 400 and 600. The same thing can be observed in N2 variation also. Maximum change in 400 and 600. There is also a change in 30 and 800, but that is mainly due to the agglomeration. The rutile phase effect can be mainly observed in 400 and 600 degrees Celsius, where there is a change in to the rutile phase of TaO2 from other phases can be visible. Then conclusion, the work detailed is an attempt to understand the effect of crystallographic phase on the thermal nonlinearity of TaO2. As the crystallographic phase changes more to the rutile form of TaO2, the linear absorption as well as thermal nonlinearity of the sample increases. That's all. Thank you.
Okay. Or can you say what is the novelty of your work? Because the same work has been published by so many people.
Hi, sir. The novelty is actually I did this work to extend it to the solar cell applications. Actually, in my PhD period, I did some solar cell works, but I used usual anatized TaO2 for the purpose to make the photoanode. But if by referring some purpose, I understood that this nonlinear absorption has a direct effect on homo-LUMO separation in solar cells. So by making this type of a tuning in optical nonlinearity, I can apply this to the solar cell area. That's the main work, but that's the future scope still. That's why I did this.
Okay. Then one more question. What is the difference between annealing and calcination? Here you use the annealing.
Calcination is just to heat the material, but annealing to vary its properties, and mainly I anneal that material in 1 hour or 2 hours for inside the furnace. But in calcination, we just anneal and remove the sample from the furnace.
No, that is not the difference. You must know what is the difference. Okay.
Okay, sir.
Sir, Franklin, sir.
So how do you calculate the linear absorption coefficient?
That is from the emergent and incident laser intensities on the sample. Log I0 by I.
Oh, okay, the basic equation.
Yeah.
Okay, thank you.
Thank you, Ria. Let's move on to the next presenter. ID number 087, MEMC CK, Mercy College, Palakkad. Presenting on the topic, crystallization of bioactive cobalt-based hybrid solids.
Hello.
Yeah, you can start.
Good afternoon, one and all. I'm MCCK, Assistant Professor, Department of Chemistry, Mercy College, Palakkad. The topic of my presentation is crystallization of bioactive cobalt-based hybrid solids. In this work, we have synthesized 2 pseudopolymorphs of cobalt chloride to aminopyrrazine complexes by solvent evaporation method. A detailed structural analysis was done by means of single crystal XRD, FTIR, TGA, and elemental analysis. The role of non-covalent interactions that stabilize the crystal packing was investigated in detail using Hirschfeld surface analysis and 2D fingerprint plots. The solids were found to possess remarkable antibacterial activity as revealed by in vitro antibacterial studies and molecular docking studies. Self-assembly of organic inorganic hybrid solids
Can you
is
show the
primarily
respective
dictated.
slides?
Yes, sir. Hello.
Hello. Still at the title slide. You may change.
Oh, okay. Is it now visible, sir?
Yeah.
Introduction slide.
Okay. It is visible. Yes,
And
visible.
while investigating the role of reaction parameters that affect the self-assembly process in the formation of polyoxomolybdate hybrid solids, we selected a heterocyclic ligand 2-aminopyrrazine as the organic precursor. However, it resulted in the crystallization of 2 metal complexes, which are pseudopolymorphs. Solids 1 and 2 were prepared by solvent evaporation method as per the scheme shown here. The obtained solids were characterized by single crystal XRD, FTIR. The thermal stability of the solids was studied by thermogravimetric analysis. From the single crystal data, it was observed that in the crystal structure of 1, CO2 plus is at the center of the octahedron, surrounded by 2 protonated aminopyrrazine moieties and 4 chloride ligands. Crystal packing in 1 is stabilized by hydrogen bonding interactions, leading to one-dimensional chains, which are further connected to form two-dimensional sheets, as shown in figure 4A and B. Apart from hydrogen bonding interactions, pi-pi interactions also stabilize the crystal structure. In the crystal structure of 2, CO2 plus is at the center of the octahedron, surrounded by 4 2-aminopyrrazine moieties and 2 chloride ligands.
And unlike in 1, here the aminopyrazine moieties are not protonated. In the structure of 2 also, there are extensive hydrogen bonding interactions, mainly NHCl interactions, leading to one-dimensional zigzag chains, which are further connected to form two-dimensional sheets. Inter and intramolecular hydrogen bonding interactions further connects the sheets to form three-dimensional network. In order to obtain a deep insight into various non-covalent interactions, Hirschfeld surface analysis were carried out. Hirschfeld surface analysis represents a novel approach for visualization of molecular surfaces and for investigating intermolecular interactions in crystals. And the presence of such interactions can be explained by mapping Hirschfeld surfaces on different properties such as d-norm, molecular electrostatic potentials, shape index, curvedness, etc. Figure 9 shows the Hirschfeld surfaces plotted on different properties, and 9a shows the d-norm surface of solid 1. And here, the bright red circular spots on the Hirschfeld surface indicates the regions involved in hydrogen bonding interactions. Similarly, in 9d, it is a shape index map. And on this, we can see adjacent triangular blue and orange patches over the aromatic ring, which indicates the presence of weak pi-pi interactions in the crystal. Curvedness is another important property represented in 9e, which indicates the planar nature of the molecules. We can also plot electrostatic potential map on the Hirschfeld surface of 1, and the red color regions indicates the electronegative regions, where the blue corresponds to the electropositive regions on the surface of 1. Figure 11 shows the Hirschfeld surfaces of solid 2, and 9a represents the d-norm surface, and 9d indicates it's a shape index map, which presents the characteristic features of pi-pi interactions in the crystal, and 11e shows the curvedness map, which indicates the planar nature of the molecule. Electrostatic potential map was also plotted on the Hirschfeld surface of 2. Another important information that is obtained from the Hirschfeld surface analysis is two-dimensional fingerprint plots. It provides a fingerprint of the intermolecular interactions in the crystal, and it gives information on the type of interaction and also the relative area of the surface corresponding to each kind of interaction. Figure 13 represents the fingerprint plots of 1, and in 1, the major contribution to the Hirschfeld surface is due to HCl interactions, contributing to about 52.8% to the total surface, and that is appearing as two sharp symmetric spikes. Figure 14 represents the two-dimensional fingerprint plots of solid 2. And in this, the HH interactions are the most abundant, contributing to about 42.9%, followed by NH interactions. The prepared complexes were also evaluated for its antibacterial activity against various bacterial strains, and it was found that solids 1 and 2 showed remarkable antibacterial activity. Molecular docking studies were also carried out in order to substantiate the in vitro results of in vitro antibacterial studies. Docking studies were carried out using Autodock software, and the results were analyzed using BioVia Discovery Studio. The protein target chosen was DNA gyrase B present in E. coli and Bacillus subtilis. Figure 16 and 17 represents docking of solid 1 and 2 respectively with DNA gyrase B present in E. coli. Figure 18 and 19 shows docking of 1 and 2 with DNA gyrase present in Bacillus subtilis. The binding free energy values indicate the binding affinity of the prepared complexes with the protein target. The higher the negative value of the binding energy, the greater will be the binding affinity. So from the docking results, it was observed that solids 1 and 2 shows a higher negative value of the binding free energies with the DNA gyrase when compared to the free ligand, especially solid 2 with the protein target 4DDQ, that is a protein ID, with DNA gyrase present in Bacillus subtilis. So solid 2 showed a highest negative value of binding energy, that is minus 6.37 kilocalories per mole. To conclude, two cobalt-based pseudopolymorphs with two aminopyrazine ligand were synthesized using solvent evaporation method. The role of non-covalent interactions that stabilize the crystal packing was investigated in detail using Hirschfeld surface analysis and fingerprint plots. The prepared complexes showed remarkable antibacterial activities when compared with the free ligand and the standard antibiotic gentamicin. In particular, 2 exhibited greater sensitivity towards all bacterial strains. Molecular docking studies were in good agreement with the results of the wet lab experiments. And from the in vitro and in silico studies can be concluded that the synthesized cobalt-2 complexes can be promising novel antimicrobial agents. Thank you.
So how do you do the antibiotic studies, and is there any, you didn't show any results from that one? Or
Actually, we measure the zone of inhibition. We measure this circular spots, no? So that's a zone of inhibition. We measure that zone of inhibition with a ruler and comparing the distances.
So did you calculate the MIC values from here, or?
No, we just did a preliminary screening. MIC values are not calculated.
How do you get this electrostatic potential surface diagram?
That is using software Crystal Explorer.
So you do a docking simulation with what software do you use?
Docking was done using Autodock, and the images were rendered using another software, BioVia Discovery Studio.
Did you do any other in vivo or ex vivo studies, or you are planning?
No, that is pending, sir. We just this is just a part of my work, and only the in vitro studies have done.
Okay, is it? Are you doing PhD?
Yes.
Okay, who is your guide?
Dr. Jency Thomas, St. Thomas College, Thrissur.
Oh, okay. Okay, thank you.
Thank you, sir.
Okay, thank you.
Thank you, sir.
Thank you, MC. Next presenter, ID number 088, Sinita B. Nair, Sri Shankara College, Kaladi. Presenting on the topic, fabrication of PCUO or NTiO2 nanotubular heterostructure for enhanced photocatalytic activities.
Good afternoon, all. Is my screen visible?
Yeah.
Yes.
Okay, you can start.
Okay. Okay. Good afternoon, all. Myself, Sinita B. Nair, Assistant Professor in the Department of Physics, Sri Shankara College, Kaladi. The title of my work is Fabrication of PCUO NTiO2 nanotubular heterostructure for enhanced photocatalytic activities. The outline of my presentation comprises of introduction, highlights, experimental and characterization techniques, results and discussion, conclusion, scope of future work. Introduction. With the worldwide technological developments, environment and energy issues become a growing challenge to the existence of living beings. Various harmful organic pollutants enter the water sources and pose a serious threat to our environment. Photocatalysis is regarded as one of the most effective and environment-friendly technology that utilizes solar light effectively to remove organic pollutants from water. The conditions for a good photocatalyst are, it must have high surface to volume ratio that offers large absorption area, high light absorption efficiency to make use of the entire solar spectrum, effective separation of photo-generated charge carriers, biocompatibility, stability of the photocatalyst, and recycling capability. Semiconductors such as titanium dioxide, zinc oxide, iron oxide, etc. all act as good photoactive materials. Among us, TiO2 has proved its benchmark as a good photocatalyst due to its high photochemical stability, biocompatibility, non-toxicity, unique optoelectronic potential, etc. properties, etc. Among various nanostructured forms of TiO2 like nanoparticles, nanorods, nanofibers, etc., the research potential of one-dimensional nanotubular structure is significantly high since it offers excellent electron transport pathways for the vertical transfer of electrical charges along the length of nanotube. It offers excellent electron hole separation properties. It shows excellent morphological, optical, and electrical properties. The three most common polymorph of TiO2 are anatase, rutile, and brucite. Anatase TiO2 is an N-type indirect bandgap semiconductor and is having a bandgap of 3.2 electron volt, which is used in charge separation devices like DSSCs and photocatalysis. However, due to its wider bandgap of 3.2 electron volt, it shows poor response to visible light absorption. Also, its fast electron-hole recombination rate leads to poor quantum efficiency. Intense efforts have been done to shift its optical response to the visible range. Band structure modification by heterostructure formation is found to be the most promising method for improving the visible light harvesting. But the modification method found in literature are based on high thermal energy budget, costly, time-consuming, and usually suffer from multiple and tedious steps. Hence, simple and cost-effective methods in low energy budget is particularly important. Highlights of this work are heterojunction construction of PCUO and TiO2 constructed by electrochemical anodization followed by impregnation method. This modified structure offers advantages of tailoring of bandgap of the nanotube to visible region, achieved a 5-fold increase in the photocatalytic efficiency when compared to undoped TON. Figure 1 shows the process flow of formation of heterostructure of PCUO and TiO2 nanostructure. Well-loaded TONs are fabricated by anodization of Ti foil in a 2-electrode system with ethylene glycol and ammonium fluoride as the electrolyte at room temperature. When these fabricated TONs are impregnated for 4 hours in a magnetically stirred solution prepared by adding copper sulfate to the aqueous solution of ethanol. The impregnated samples are annealed for 2 hours at 450 degrees Celsius in air to obtain the modified PCUO and TiO2 structure. These are the characterization techniques done. Moving to the results and discussion. First, morphological analysis. The micrograph reveals a perfect tubular structure for the TON. The surface morphology of the prepared CuO TON analyzed from FE-sum indicates thickening of the boundary walls. However, the tubes are not blocked and the tubular structure is still retained. Figure 3 shows the EDAX spectrum and it contains Ti, oxygen, and small percentage of copper is incorporated in the sample. Figure 4 shows the XRT pattern of TON and CuO TON. The peak around 25.3 degree, 48.1 degree, 53.9 degree, and 68.7 degree correspond respectively to 101, 200, 105, and 116 crystal planes of anodized TiO2. In addition to this intense peak, low reflection peaks are observed around 35.6 degree and 48.8 degree in CuO TON structure. These are identified as the reflection from 002 and 202 planes of copper oxide. And it indicates the formation of both copper oxide and TiO2 phases. This is the optical studies. Diffuse reflectance spectroscopic analysis is done to determine the optical bandgap of this sample. Optical studies in figure 5 indicates that a reduction in bandgap from 3.2 electron volt of anodized TON to 2.36 electron volt for the modified structure. The current voltage characteristics of TON and CuO TON is shown in figure 6. TONs do not show any rectifying behavior, but CuO TON exhibit very good rectification. The significance of this PN heterojunction formation is in its ability to provide charge carrier separation. And it is seen from figure 7 that within the time span of 180 minutes, about 75% of photo degradation of methylene blue is achieved for the active solution. A maximum of 5-fold increase in the degradation rate for methylene blue is obtained with CuO TON than pure TON. And the enhancement in photocatalytic activity can be ascribed to 3 important factors: the creation of a PN junction that provides an internal electric field that helps in the separation of photo-induced electron-hole pairs, increased absorption of visible photon due to the reduced band gap, and the creation of more active absorption sites by the small size of copper oxide nanoparticles and the large surface to volume ratio of the heterostructure. The photocatalytic mechanism is shown in figure 8. CuO TON respond to light radiation producing the electron hole pairs. The photo-generated electrons and holes are moved in the opposite direction at the junction and enable effective separation of the electron hole pairs. The potential barrier at the junction help in building a space-charge separation for the longer time. The electrons on the N-TiO2 react with O2 absorbed on the surface to form the superoxide radical, whereas the photo-generated holes left in the valence band react with water molecule to yield highly oxidative hydroxide radical, which is a strong oxidizing agent to decompose the dye. This reactive radical combined with organic compounds to form carbon dioxide and water. Moving to the conclusion, this work focuses on the fabrication of PCUON TiO2 type 2 heterostructure by simple, cost-effective and time-saving electrochemical anodization followed by impregnation method. Prepared CuO tone shows superior photocatalytic activity for methylene blue due to its lowered band gap energy and increased charge separation. The rate of photocatalytic activity of PCuO and TiO2 is 5 times greater than that by the pure tone. Scope of the future work. This study lays the foundation for many future work that can develop highly efficient photocatalysts. The band gap tuning and conductivity enhancement presented in the work make them potential candidate for other energy and environmental applications like water splitting, DSC supercapacitors, etc. The prepared techniques employed in the current study can be directly applied to other application areas as well as to other metal oxide semiconductors. Thank you.
Okay, your work is good. Then the question is, why did you choose only methylene blue for photocatalyst studies?
As the next part, I want to try for other dyes, etc. Sir.
Okay.
Methyl orange, Congo red, etc.
Okay.
For this work, I tried only this methylene blue.
Then, how did you study the photocatalysis?
I prepared this methylene blue dye and put this sample in the methylene blue dye and placed under this sunlight for 3 hours. For different times, that is for 15 minutes, 30 minutes, 60 minutes, 120 minutes, and 180 minutes for different time periods.
Okay, what is the intensity of sunlight?
That I
Okay.
I think it's
as a physicist, you must ensure that the intensity should be stable.
Okay, sir.
Okay, 180 minutes. That much is the highest value. Okay. Sir, can you please?
What do you expect? So this, you have observed methylene blue degradation. So can this be used as a DNA intercalator, chelating agent, something like that? Do you have any idea?
No idea, sir. Sorry, sir.
Okay, thank you.
Okay. Thank you very much, sir.
Okay, thank you.
Thank you, Sinita. Next
Okay,
presenter, ID number 089, Vinita N, Vimala College, Thrissur. Topic is structural and optical characterization of zinc aluminate nanoparticles synthesized via green microwave route.
Good evening, ma'am. Am I audible, ma'am?
Yes.
Audible.
Thank you, sir. Once again, good evening, everyone. I am Vinita N, presenting the current work under the guidance of Dr. Minikrishna K from Department of Physics, Vimala College, Thrissur. The topic of study is on the structural and optical characterization of zinc aluminate nanoparticles synthesized via green microwave route. Zinc aluminate, which is the material of present study, has many advantages like high chemical stability, high quantum yield, good fluorescence efficiency, strong thermal and mechanical resistance, wide surface area, low surface acidity, and also it is a direct bandgap semiconductor with a bandgap of 3.8 electron volt, and it is useful in dielectrics, optics, and sensors, and many other applications. But the high temperature synthesis and the use of very toxic chemicals limits its industrial applicability and make it very expensive. Here lies the importance of green synthesis. Actually, the advantages of green synthesis are it is very environment friendly because it replaces the use of toxic precursors, and also it improves the monodispersive nanoparticles, modulates size and shape, and also it reduces the time for synthesis at a very low cost. Here, plant extracts are the main thing, which serve as reducing agents for metal cations and also stabilizes the synthesized particles. Now we will move on to the experimental procedure of the present work. Here the precursors used are zinc nitrate and aluminum nitrate, which are mixed, and to that mixture a plant extract, which is the extract of freshly cut open-shade aluminum leaves, is added, and it is heated in a microwave oven with these given specifications. Actually, I have prepared 4 samples with the 4 different precursors ratios. The duration of synthesis is lowered to just 10 minutes. And now moving on to the results. First, I have done the XRD analysis in order to check if the structure is formed or not. And the equipment which is used for the XRD analysis is Bruker D8 Advanced X-ray diffractometer. And the as prepared samples show spinels, peaks corresponding to the spinels in aluminate, even without post annealing, but it is not perfect. So in order to make it completely spinel structure, we have to do firing, that is calcination. Also the distinctive spinel peaks corresponding to zinc aluminate, which loses its intensity on increasing the zinc content. To substantiate XRD results, FTR spectra is also done with the Shimozu air spirit spectrophotometer, and there is a band which is at 533 centimeter raised to -1, which corresponds to the infrared active mode of ALO stretching vibration, which is actually corresponds to the ALO6 group, which builds up zinc aluminate spinel, and also the peak becomes the peak becomes stronger with the decreasing the zinc amount. And also we can see a peak at 1370 centimeter raised to -1, which is corresponds to the NO2 group, which may be due to the existence of leftover plant extract, since our sample is not calcined. And the bands which appear in the range 700 to 1000, which will be correspond to the organic molecules which is leftover in the sample. And also the samples with a less zinc amount shows much intense peaks. And in order to find out the band gap, we have done the DRS spectral analysis, and we can observe a shift, blue shift from the bulk band gap energy, that is 3.8 electron volt is observed here. These are the band gap values corresponding to all the 4 samples, and the sample with the high zinc content have a band gap in the range 3.04 electron volt, which is corresponds to the zinc oxide, which is present in the sample. And also there is some fluctuation in the band gap energy, which may be due to the quantum confinement effect, because the band gap drops as crystallized size grows. And also there are some shoulders in the DRS spectrum, which may be due to the lattice faults. And now coming to the photoluminescent analysis, we can see UV and blue emission at an excitation of 300 nanometer, which is a typical property of undoped zinc aluminate, which is the best photoluminescent response is observed for the sample with the less zinc content. And also this is substantiate the structural analysis, XRD and FTR. Now, in order to check whether the formation is happening on calcination, we have calcined one sample, which is the first sample, that is with low zinc content. We have calcined the sample at 450 degree for 2 hours, and as expected, the presence of all prominent spinel peaks of zinc aluminate is observed here, which is well agreement with the standard data. And here average crystallized size is calculated. It is as 4.428 nanometer, which is using the Debye-Scherrer equation. In order to confirm this structural formation, we have done the TEM analysis, and from the TEM analysis, the lattice parameter is calculated. And these are the conclusions of the present work. The present work, microwave assisted green synthesis, which is found to be very reliable and cost effective for producing nanocrystalline zinc aluminate. And the advantage is that the synthesis duration can be drastically reduced. And also the spinel formation on calcination at a very low temperature, that is 450 degrees Celsius, is we can form this phenol at this very low temperature, which is confirmed from XRD and TEM measurements. And also the structural analysis are supported by PL emission, and also from the DR spectrum, we have got a very good band gap, that's 4.85 and 5.2, 5.04 in the range, 4.85 to 5.04. The band gap tuning is possible and it is very useful in optical device band gap engineering. And the post annealing improves the crystallinity. And these are the references supported this work. And we thank DST Phys Lab, Postgraduate Research Department of Physics, Vimala College, Thrissur. And I personally thank KSCSTE for the research fellowship. And thank you so much.
Okay, what is your source of this plant extract? From what?
Sir, the plant extract is actually from Opentia dialyme plant leaves.
So you will have many many type of molecules, ions inside the plant extract, including lipids, proteins, and everything. How do you make sure that a particular material from your plant extract is doing this reduction to form this nanoparticle?
Sir, actually, we have to study the extract by phytochemical reactions such that actually the work is pending, sir. I have to study more about plant extract, why it is making this this kind of work.
Okay, this type of extracts, I mean, exactly this extract was used, reported in literature?
Yes, sir. Already it is reported in synthesizing some silver nanoparticles and some aluminum nanoparticles, etc. So I have tried this extract for synthesizing my material.
What is the particle size which you observe from TEM analysis?
So this is the results from TEM analysis, and this is the value of lattice parameter. It's in good agreement with the JCPD's value.
Average crystalline size 4.424, 428.
Yes, sir. Yeah.
Okay, thank you.
Okay, why did you choose 450 Celsius or your calcination temperature?
Yes, sir. Actually, I had done the TGA TT analysis before for the sample.
But you didn't mention anything about TGA analysis?
Sir, actually, that was my previous work. So I have not included it here. I actually have tried 4 different temperatures for the post annealing, and also I had done the TGDT analysis. From that, I have fixed this temperature.
Okay. Thank you.
Thank you, sir. Sir, can I leave?
Yeah, you can.
Thank you, Vinita. Next presenter, ID number 090, Meenu Eldos, Newman College, Thodupuzha. Presenting on the topic, zinc tungstate or reduced graphene oxide composites for electrochemical sensing of dopamine.
Good afternoon, sir. Can I share my screen?
Yeah. You can continue.
Is my screen visible?
Yeah, visible.
Okay. Okay. Today, I'd like to present on my topic, zinc tungstate reduced graphene oxide composites for the electrochemical sensing of dopamine. And me, myself, Meenu Eldos, research scholar, Department of Chemistry, Newman College, Thodupuzha, and under the guidance of Dr. Cincy George and Alex Joseph. And here I have chosen this material, that is zinc tungstate. Why zinc tungstate? It's because of its optical properties, high electrocatalytic activity, good magnetic and electrical properties, improved sensitivity and response time, facile synthesis, photocatalytic and luminescent properties. All these properties have attracted me towards this particular material. And in addition to that, there are, to enhance the property of zinc tungstate, different strategies such as modulating crystallinity, tuning morphology, and ion doping, etc., has been done so far. So by here I have done or modified the zinc tungstate by using reduced graphene oxide, and by adding reduced graphene oxide or to this material, it will increase the surface area and thereby results in more active site in the electrocatalyst. And here I use dopamine and as an analyte for sensing application, because dopamine is an organic molecule which is essential for the proper functioning of central nervous system and hormone balancing. In addition to that, deficiency may cause several low levels of dopamine may cause Parkinson's disease or other diseases as well. And the electrochemical sensors are best for sensing dopamine because it is an electrochemically active molecule, and the electrochemical techniques are considered to be simple and as well as very sensitive in nature. Abstract. Here, I have synthesized zinc tungstate reduced to graphene oxide and zinc tungstate reduced to graphene oxide composites. And the corresponding characterization was done by using XRD, FTER, SEM, TEM, and Raman analysis. The electrochemical activity of zinc tungstate and reduced to graphene oxide as well as these composites was also checked towards the dopamine sensing. And the synthesis procedure which I have employed for the zinc tungstate include: the synthesis was carried out by aqueous solution growth or precipitation method, and about 5 millimole of zinc acetate and corresponding sodium tungstate was dissolved separately in about 30 ml of water separately, and after that it is mixed together under constant stirring for an hour, and the resulting white precipitate was obtained, and it is then washed and dried properly to obtain the sample. Synthesis of reduced graphene oxide, and the graphene oxide was prepared from exfoliated graphite powder by modified Hammer's method, and yellow precipitate of graphene oxide that's obtained was washed several times with distilled water and HCl in order to make it neutral. And the neutral solution of graphene oxide was then treated with 100 millimolar sodium borohydride solution and is magnetically stirred for about 3 hours. And the black colored precipitate was then washed with the distilled water and dried to obtain the reduced graphene oxide. Then how the synthesis of zinc tungstate or graphene oxide, reduced graphene oxide composites was done, it is explained here. And the different compositions of RGO, means about 4% as well as 2% we have prepared, was prepared by weighting the composition of reduced graphene oxide. And moving on to our result and discussions, here I have shown the XRD of both zinc tungstate and zinc tungstate RGO. I have only included the 4% result of XRD because that is much more electrochemically active. So here, first figure represents, first one represents zinc corresponding XRD pattern obtained for zinc tungstate, and second one represents that of XRD picture obtained for zinc tungstate RGO reduced graphene oxide composites. And it is clear that the intensity, the clear-cut intensity of zinc tungstate has been reduced, as well as the crystallinity is also changed to some amorphous character. Here we are modifying with about 4% of RGO at the maximum. So in addition to that, an extra peak has been appeared, shows for this reduced graphene oxide at a 2 theta of about 23 degree. And moving on to FTR, and since this A, B, and C represents the Fourier transform infrared spectroscopy for zinc tungstate RGO composite, and reduced graphene oxide respectively. And here all the peaks for all peaks are almost the same for both. That is, this RGO shows a band at 3500 because of hydrogen bonding, and similar is the case with that of zinc tungstate, because here we are synthesizing this material in aqueous solution, so it will also shows a particular peak, means FTER peak at 3500 something range. And this is a Raman analysis spectra which I have got for zinc tungstate RGO and corresponding zinc tungstate RGO composite. It is more clear that the composite formation has been done. It is clear from this Raman analysis, that is for the zinc tungstate it has only one peak, and for RGO both the D and G bands is also present, and for zinc tungstate RGO composites both the composite present zinc tungstate peak as well as the peaks of RGO were also found here. And these are the same images, and from the same images there is no such no much information can be arrived, but we can see the coating, means the dispersed itself, it is dispersed on the surface of RGO. And this is the EDAX pattern analysis of zinc tungstate and zinc tungstate RGO 4%. And it is clear that here for zinc tungstate, the elements zinc, tungsten, oxygen, etc. were present. But in the case of zinc tungstate RGO composite, here the carbon as well as the oxygen is also present. In addition to that, the intensity has also slightly increased. And this is the elemental composition of from the EDAX pattern. And these are the TEM images, and this is for the zinc tungstate alone, and this is for the RG alone, and this is for the composite. And it has been seen that it is spread on the zinc tungstate nanoparticle has been spread on the surface of this graphene oxide, reduced graphene oxide. Then for electrochemical sensing, here we are using carbon-based electrodes as for coating. So we have prepared the carbon-based electrodes in our lab, and the graphite powder is mixed with paraffin oil in 7:3 ratio and is ball milled for about 72 hours. And the carbon paste so prepared was filled in a glass tube at a height of around 1 centimeter, and the silver wire was inserted for the electrical contact. The CP electrodes was chemically modified using pristine zinc tungstate RGO and zinc tungstate RGO 2% and 4% respectively. And the corresponding electrochemical studies were done, and this represents a CV of bare zinc tungstate and zinc tungstate RJ 4% and 2% and 4% respectively. And this was done by using acetate buffer with a pH of about 4.8, and dopamine was used at analyte, and the concentration is about 0.01 molar. And in addition to that, KNO3 is used as a 0.1 molar KNO3 is used as a supporting electrolyte, and the potential window ranges from -0.7 to +0.7 volt, and it is done at a scan rate of 0.1. And before moving on to DPP studies, it is necessary to fix the pH of that particular solution for getting the maximum peak height. So the pH studies were also done by using DPV technique. And so from this figure, it is clear that from this profile, it is clear that the pH is pH is 4.8 has a maximum current. So we have fixed pH as 4.8 for the upcoming studies. And this is a DPV analysis of CPV, zinc tungstate RJ 4%, because I have done the DPV analysis of 4% alone, because in the graph of CV, the 4% shows the maximum peak height. And so the DPV analysis was done by using this particular CP, zinc tungstate RJ 4% composites only. And here the DPV represents a composition ranging from 0.1 millimolar to 0.01 millimolar dopamine in the presence of 0.1 molar KNO3 as the supporting electrolyte in a acetate buffer of pH 4.8, and the potential varies from 0.15 volt to 0.6 volt. And the corresponding linear fit graph were also obtained, and Pearson's as well value was obtained about 0.9967. And the most probably indifferent studies should be necessary for carrying out the sensitivity of a particular composites, sensitivity of composites towards various analytes such as ascorbic acid, glycine, creatine, glucose, etc. All these parameters were present in our blood serum. So it is necessary to analyze how these will affect the sensing ability of that particular one. So we have done the indifferent studies by taking 1:0.1 equivalent of dopamine and corresponding interfering species, and the analysis were carried out, and ascorbic acid seems to be the most interfering, and almost all others are seems to be about interfering, because they they are actually affecting the peak height of the particular composites. And the major conclusions which I have arrived is that in the present work, we fabricated a non-enzymatic low-cost electrochemical sensor for the detection or electrochemical detection of dopamine. And the synthesis was very simple, and because it is carried out by using zinc tungstate RJ composite, was carried out using co-precipitation method. And physiochemical properties of this pristine tungstate and reduced graphene oxide and zinc tungstate composites was carried out using XRD, Fourier transfer, TER, scanning electron microscopy, and TEM and Raman analysis. And the electrochemical analysis was done by using PV and DPV techniques, and it shows excellent activity towards the detection of CA and shows high sensitivity with a correlation coefficient of R² of 0.9967. And these are the references which I have used for this. And I sincerely acknowledge all my team members, as well as especially my guides, Dr. Sinsi George and Dr. Alex Joseph, for the wholehearted support given to me. In addition to that, I would like to acknowledge the financial support from the MG University Kottayam in the form of University JRF Fellowship for the work. And thank you.
Thank you. It was nice work. Did you compare the non-dopamine sensors, which is already a with what is your
1 second. Actually, I'm planning to do, whether it is possible, I don't know. I'm planning to do a real-time analysis. So I have compared with calculated the LLOD, and it has been about 4.63 micromolar, which is in best result as it is not reported so far.
Okay, did you check the possibility of these compounds in passing the blood-brain barrier, because dopamine sensing?
Sir, actually, I haven't checked it now, but I would like to check it, or I'd like to do the real-time sensing if possible. I'm detailing about that.
Okay, thank you.
Okay, thank you.
Thank you, Meenu. Next ID number 091 Drishya V NIT Caricat, presenting on the topic FMOC phenyl alanine based
Let us go for the next presentation.
fluorimetric and colorimetric dual channel probes for the detection of Fe3+, Ce2+, and F-. Hello. Hello, sir, audible?
Yes, we can see the slides, but it's not moving.
It's not moving. Okay, so 1 second.
Okay, okay.
So whether it is in slideshow mode or it is in.
This is also fine. You can go forward.
So now it's okay?
Yes.
Yeah, it's okay.
Yes. Good afternoon, everyone. Myself, Drishya V, research scholar working under the guidance of Dr. Lakshmi C, Professor, Department of Chemistry, NIT Calicut. My work include phenylalanine based fluorimetric and colorimetric dual channel probe for the detection of Fe3+ and Cu2, detection of Fe3+, Cu2+, and F-. So coming to our main focus is on the fluorimetric sensors or fluorescent sensors. Moving to the fluorescent sensors, what is a fluorescent sensor? As
Can
we
you
know,
move on to the next slide?
so it's not moving?
Not moving.
Oh, sorry, sir.
Okay, now it's okay. Okay, carry on.
Okay, sir. Now it is moving, right, sir?
Yeah.
Okay. So a molecular sensors, coming to molecular sensors, a molecule which can undergo or which can produce a readable signal on interaction with various analyte either through host-guest interaction or any chemical transformation
We cannot see the slide. We can only see the text introduction.
You just click on the
Yeah.
Now it's okay, sir.
Now it's okay.
Okay. A sensor is a molecule that can produce a readable signal on interaction with various analyte, either through host-guest interaction or chemical transformation are called as a molecular sensors. Coming to fluorescent sensors, these fluorescent sensors can be classified into chemosensors and chemodosimeters. And the sensors which undergoes sensors which reversibly interact with various analyte to produce a readable signals are called as chemosensors. Normally, a chemosensor consisting of a signaling unit and a recognition unit connected through a linker. The emission profile of the signaling unit is controlled by the interaction of this recognition unit with a specific analyte. So in this example, we can see that the interaction of this recognition unit with a specific cation control the emission profile of the signaling unit. And coming to the chemodosimeters, the sensors which irreversibly undergo a structural modification in presence of various analytes termed as chemodosimeters. So in chemodosimeters, it is mainly based on the reaction-based mechanism, and these are two examples of chemodosimeters. And we are mainly focusing on fluorescent sensors, various analytical detection techniques are developed for the selective and sensitive detection of various analytic abload, which include atomic absorption spectroscopy, flame atomic absorption spectroscopy, inductively coupled plasma mass spectrometry, etc. But these techniques are expensive, complex, require trained personnel, and need laborious sample preparation. But nowadays, fluorescent detection technologies have gotten greater acceptance due to its good selectivity, sensitivity, quick response, and low cost. So we are focusing mainly on the fluorescent-based molecule for the detection of various analytes. So as we know, the heavy metal ions plays a crucial role in different biological process, and the strict regulation of their concentration require the proper functioning of any organism. Any deviation from the permissible level in their concentration can lead to different physiological condition. Among these heavy metal ions, iron and copper plays a very important role in different biological process. Iron helps in the formulation of hemoglobin, muscle activity, immune system development of brain and brain development and functioning, thyroid functioning, oxygen uptake and metabolism, electronic transfer, synthesis of DNA and RNA, nervous conduction, proton transfer, enzyme synthesis, etc. The iron deficiency adversely affect different parts of the body, include heart, brain, stomach, etc. Similarly, copper also help in the growth, immunity development, digestive system, proper functioning of digestive system, and as a part of antioxidant, and is helping the proper functioning of nervous system also. And the copper poisoning also adversely affect different parts of the body, include liver, eye, skin, kidneys, mouth, circulatory system, etc. So the development of fluorescent sensor for the selective and sensitive detection of these heavy metal ions are of most important. Hence, we designed 4 ethmophenylalanine based chemosensors for the selective and sensitive detection of Fe3+ and Cu2+. The designing of this molecule consisting of connecting ethmophenylalanine to either naphthalene or pyrinamine through amide or amide triazole linkage. Then the synthetic route involves the EDC coupling of the ethmophenylalanine with the corresponding amine, that is naphthyl, pyrene, or propagylamine, to yield the corresponding amide linked derivative. The propagyl derivative under click condition to produce the corresponding amide triazole linked derivative. Then we have recorded the both absorption as well as emission spectra of all the 4 compounds, and both the naphthyl derivative exhibited similar absorption as well as emission spectra. Similarly, both the pyrene derivative also exhibit similar absorption as well as emission spectra. All the 4 probes respond similarly towards various analytes and various conditions. Here we are using FPAPY as a representative example. Then we have performed the selectivity experiment towards Fe3+ and Cu2+. We recorded the fluorescent response of these molecules in various metal ions in presence and absence of Fe3+ and Cu2+. In presence of the fluorescent intensity of the probe conscious only in presence of Fe3+ and Cu2+, and other metal ions are failed to elicit such changes. And also any other okay, these are the corresponding photographs of FPAPY in DMSO containing various metal ions under 365 nanometer UV lamp and under normal light. Here we can see that the fluorescent intensity of the probe conscious only in presence of Cu2+ and Fe3+. So then moving to the fluorimetric and colorimetric titration experiments, here we can see that with the gradual addition of Fe3+ or Cu2+ to the probe solution, the intensity of the probe decreases gradually. So then we calculated the limit of detection, and the limit of detection of FPAPY towards Fe3+ was found to be 1.88 micromolar, and that towards Cu2+ is found to be 3.12 micromolar. Then we have performed a colorimetric titration experiment with a gradual addition of Fe3+ or Cu2+ to the probe solution. The absorbance of the probe increases gradually. So then we have performed the Stern-Volmer analysis and Jobs plot analysis. Then Jobs plot analysis revealed that all the probe prefers a 1:1 binding stock Fe3+ and Cu2+. Further, we analyze the utility, or further we investigate the utility of probe Fe3+ for the detection of fluoride ion. As we know, the fluoride ions are known to form a thermodynamically stable FeF or resulted in the emission quenching of the probe. Any decomplexation with the formation of FeF6 3- with the addition of fluoride ion to the probe Fe3+ complex may resulted in the restoration of the fluorescent intensity of the probe. So this is a photograph of FPAPY Fe3+ complex containing various anion under 365 nanometer UV lamp. Has been from the figure itself, it is very clear that only in the presence of fluoride ion, the emission intensity of the probe regains. Then we have performed the fluorimetric titration experiment, and we added fluoride ion source to we gradually added fluoride ion to the probe Fe3+ complex, and it's very clear from the figure. The emission intensity of the probe increases gradually with the addition of fluoride ion, and the limit of detection was found to be 0.64 micromolar. Further, in order to confirm the decomplexation mechanism, we have performed the colorimetric titration experiment. With the gradual addition of fluoride ion to the probe Fe3+ complex, the absorbance of the probe decreases gradually, suggesting the decomplexation mechanism. Then we have performed the reversibility studies with the alternate addition of Fe3+ and fluoride to the probe solution. We recorded the emission spectra. With the addition of Fe3+, the intensity of the probe decreases, and with the addition of the reversal happens with the addition of fluoride ion. This cycle is repeated in an alternative manner and confirm the reversibility of this probe. Then practical utility of the probe was demonstrated by coating the probe on solid surfaces, and the probe coated filter paper is used for the quick screening of Fe3+, Cu2+, and fluoride ion. These are the corresponding fluorescent photographs of filter paper strip before and after treatment with the respective salt solution under 365 nanometer UV lamp. In conclusion, we have designed, synthesis, and characterized 4 ecmophenylalanine-based fluorophores. Preliminary photophysical properties of this molecule in solution state were evaluated. All the 4 fluorophores shows a quenching behavior in presence of Fe3+ and Cu2+ ion with good selectivity and sensitivity. And the limit of detection of all probe towards Fe3+ and Cu2+ was found to be in the lower micromolar range. And all the 4 probe prefers a 1:1 binding stoichiometry towards Fe3+ and Cu2+. The probe Fe3+ complex can be used as a sensor for the detection of fluoride ion in solution state via Kanon fluorescent mechanism. Thank you.
Thank you. It was a nice work.
Thank you, sir.
So what is the role of this naphthyl moiety when you have a phenyl FMOC group already there? Don't they do quenching in between?
No, actually, sir, we need one binding unit for sensing any metal or any anions. So FMOC itself can't bind. Also, we can increase the fluorescence.
What kind of binding is it? Is it stacking interaction, or is it electrostatic interaction, or?
So it's a kind of host-guest interaction, that is coordination type of interaction.
Oh, okay. But you have, in fact, the FMOC group and naphthyl, both are potential fluorophores, right?
Yes, it is just to increase the fluorescence of this probe. We are incorporated this pyrene and naphthalene unit.
Okay. So the synthesis is also already reported in publication, right?
Same molecule is not reported, sir. The synthetic route is already published, but the same molecule is not yet published.
Okay, okay, great.
Thank you.
Thank you.
Okay, thank you.
Thank you, Drishya. Next,
Thank you.
ID number 092, Jinsey Matthew, School of Chemical Science, MG University. Presenting on the topic, blue emissive carbon dot solution as dual mode sensor towards copper ions detection. ID number 092, Jinsey Matthew.
He is not available.
Not present in the meet.
Okay. So go for the next.
Okay, sir. Next, ID number 093, Soumya Kuriakos, St. Peter's College, Kolanjeri. Presenting on the topic, studies on the effect of TB doping on the structural and optical properties of La2 and 3 nanoparticles.
Okay, you can start. No voice.
Your sound is mute.
Soumya Kuriakos, please start your presentation.
Soumya, can you start the presentation?
Sometimes problem with net.
Okay.
Somewhere you please start. Can we move on to the next presentation? By the time she has to correct her problem.
Sir, shall we start with the next?
Yeah.
Okay.
That's
Next
Final
presenter, ID number 094, Divya Rajan, St. Peter's College, Kolanjeri. Presenting on the topic, thermal diffusivity measurement of Fe2O3 AU nanofluid composite using thermal lens technique.
Am I audible now?
Yes.
Is my screen visible?
Yeah, visible.
Good afternoon all, and welcome to my presentation on thermal diffusivity measurement of Fe2O3 AU nanofluid composite using thermal lens technique. Myself, Divya Rajan, Research Scholar in Physics, St. Teresa's College, Ernakulam, under the guidance of Dr. Shanti A. My presentation is structured as follows: introduction, synthesis, characterization, thermal diffusivity study, results, and conclusions. Thermal diffusivity is a material-specific property which describes how quickly the material reacts to change in the thermal environment. Thermal diffusivity has significant role in heat transfer devices, in coolants, and in cancer treatment. A high value of thermal diffusivity is an indication of effective heat transfer through the medium. The findings that solids have higher thermal conductivity than liquids paved the way to a new class of heat transfer fluids called nanofluids, where nanoparticles got properly dispersed in a base fluid. There is a possibility for enhanced heat transfer through the nanofluid because of the special thermophysical properties due to the presence of the nanoparticles. So here, we are focusing on a thermal diffusivity measurement using a novel nanofluid composite. When we think about nanoparticles for preparing nanofluids, it will be more advantageous to prefer nanocomposites, which has got combined physicochemical properties of the multi-materials with potential applications. Gold nanoparticles are so special because of their surface plasmon resonance and attractive optoelectronic properties. As gold is an expensive metal, it is feasible to think about a companion which is less expensive, still has significant applications. Definitely, iron oxide can serve as a promising candidate, which is economical, non-toxic, biocompatible, and environmental friendly to be paired with gold for advanced applications. So we have synthesized a nanofluid of iron oxide and gold by a simple wet chemical method, where iron oxide, chlororic acid, and trisodium citrate were used to form a nanocomposite of Fe2O3 AU. The synthesis technique is depicted in the figure, which explains the chemical reduction process to form the nanofluid composite. After synthesizing, we have confirmed the formation of nanocomposite through various optical, morphological, elemental, and structural characterization, of which a few are to be discussed here. This is the UV visible absorption spectrum of the nanocomposite. Iron oxide exhibits a broad UV visible absorption. The peak at 352 nanometer result from the ligand to metal charge transfer transition of iron oxide. And a significant peak at 525 nanometer can be attributed to the plasmonic peak of gold nanoparticles. Morphological characterization of the sample was done through EFism. The image shows a nearly spherical, still non-uniform distribution of particles in the composite. EDAC spectrum also confirmed the presence of iron, oxygen, and gold in the prepared sample. After getting confirmation regarding the formation of nanocomposite, we have done the thermal diffusivity study. Thermal diffusivity of a nanofluid can be measured using different techniques, of which thermal lens is one of the most advantageous for measuring the photothermal parameters during heat transfer. It is a high sensitive, minimum sample required, accurate, non-contact, and non-destructive technique. Lasers makes it possible to observe and understand certain phenomena which were otherwise not feasible using ordinary source of light. Laser-induced photothermal technique is a very sensitive technique which can measure even very small refractive index changes across the beam width resulting from temperature variation. A laser beam can thermally induce refractive index changes, which is the fundamental principle behind thermal lens spectroscopy. A Gaussian beam, that is a laser beam, is incident on a sample, which will excite the sample, resulting in non-radiative relaxation. Thus, heat will be generated inside the material, which is found to be maximum along the axis of the cylindrical beam waist. As a result, the temperature generated will force the molecule of the material along this axis to move towards the periphery. The spreading of molecules result in a change in the refractive index, which will result in the formation of a lens-like optical element termed as thermal lens. If a concave lens is formed, we can observe a thermal blooming through a detector. This can be used to investigate the thermo-optic properties of the sample, which is called the thermal lens technique. This is the block diagram of the thermal lens setup, and below given figure is the setup which we have used in our lab. We have used a dual beam pump probe mode match technique for this experiment. That is, the generation and detection of thermal lenses achieved separately by the pump and the probe. In mode match technique, both the beams are found focused by the same lens so that the radii of the pump and probe beams are similar within the sample. We have used a DPSS continuous wave laser of 488 nanometer with maximum power of 50 milliwatt as the pump for the generation of thermal lens. And the detection was done using a helium neon laser, which is of 632.8 nanometer for detecting the output. Required neutral density filters were used to lower the power of both pump and probe to avoid spherical aberrations due to the interference in the transmitted beam at high powers. Both pump and probe are made collinear in the mode matched configuration so that the beams propagate coaxially, which can create longer interaction length and better sensitivity. A mechanical chopper is used to modulate the pump beam intensity, and the changes in the probe beam intensity were monitored through a photodetector, which is connected to a DSO. The photodetector gives the intensity of the output probe laser beam, which is given by the decay equation given here. Thus, the time-dependent intensity is measured and fitted to get the intensity profile. Then the time response of the thermal lens can be used to determine thermal diffusivity using the equation D is equal to omega f square by 4 Tc, where omega f is the beam spot size and T is the characteristic time constant. Figure shows a typical thermal lens obtained in the DSO. We have standardized the experiment using water, whose thermal diffusivity is obtained as 0.143 into 10 raised to minus 6 meters per second, which matches thermal diffusivity of the nanofluid. Here, the first figure shows the decay curve of 0.15 ml of nanofluid from the intensity versus time graph. And second graph is the thermal diffusivity versus concentration graph of nanocomposite at various concentration per 3 ml of base fluid. It is clear that the thermal diffusivity shows an enhancement initially, which is about twofold of that of base fluid at a particular concentration in our experimental range. After that, it shows a decrease, even which is better than the base fluid. The initial enhancement can be explained using Brownian motion, where the convection in liquids induced by Brownian motion of nanoparticles enhances diffusion. After a particular concentration, there is a possibility for cluster formation due to van der Waals attraction, which can reduce the molecular distance and causes a reduction in diffusivity. Here are the conclusions. We have successfully synthesized iron oxide gold nanofluid composite, and the formation is confirmed through various characterization techniques. Thermal diffusivity study showed a specific pattern of an enhanced thermal diffusivity at a particular concentration, from which we can find an optimum value for maximum thermal diffusivity. Here are the applications in high-performance thermal transfer liquids, in thermoelectric coolers, and in cancer treatment like photodynamic therapy and magnetic hypothermia. These are my references. Thank you.
Okay, here you have some applications, but
yes, sir.
To undertake any application study?
So we have done the photodynamic therapy study of this nanocomposite, and it is found to be applicable in photodynamic therapy.
Okay. Then what is the novelty of your experiment?
Actually, thermal diffusivity measurements using single nanoparticles have done, but the main focus is always on thermal conductivity measurement. But most of the time, we may not be obtaining the actual values as expected. So, if we can measure the thermal diffusivity instead of thermal conductivity, then we can a transient heat conductivity measurement can be possible. And also using this nanocomposite, not much work is done so far.
Okay. This is the first measurement.
Regarding this composite, I haven't found any other paper, sir.
Okay. Franklin, sir.
Thank you.
Okay. So for the next.
Okay, sir. Thank you.
Thank you, Divya. Next, ID number 093, Saumya Kuriakos.
So may you please unmute your mic.
Sir, am I audible?
Yeah.
My presentation studies on the effect of terbium doping on the structural and optical properties of lanthanum tungstate nanoparticles. Myself, Saumya Kuriakos, doing research under the guidance of Dr. Thomas Verghese, Newman College, Thodupuzha. The objective of this presentation is to explain the synthesis of pristine lanthanum tungstate nanoparticle and terbium doped lanthanum tungstate nanophosphor by chemical precipitation method, and also to investigate the effect of terbium doping on the structural and optical properties of the synthesized nanoparticles by using various characterization techniques. Next slide. The rarer based tungstate have an important role in the display field and lighting device because of their abundant emission colors and other unique structural and optical properties. Lanthanum tungstate nanoparticles have monoclinic scheelite-like structure, and the terbium ion is used as dopant here. They are most widely used green emitter in the doped substances. By tuning the size, shape, and composition, the materials having new desirable properties can be explored. These are the characterization techniques we use. The structural properties of samples were studied using X-ray diffraction techniques and scanning electron microscopic techniques. Energy dispersive X-ray spectroscopy reveals the elemental composition of sample. Optical properties of the prepared sample were analyzed using UV visible absorption spectroscopy and photoluminescent spectroscopy. About the synthesis, we synthesized pure and 5 mole percentage terbium doped lanthanum tungstate nanoparticle by chemical precipitation method. For this, analytical grade chemicals such as lanthanum nitrate hexahydrate, sodium tungstate dihydrate, and terbium nitrate hexahydrates are used. In this presentation, pristine sample is termed as TB0 and doped sample is termed as TB5. Then move on to the sample preparation. This is the schematic representation of the synthesis procedure. Initially, 0.1 molar solution of lanthanum nitrate and sodium tungstate were dissolved in 100 ml of distilled water separately. The sodium tungstate solution was added to the lanthanum nitrate solution under constant stirring for 15 minutes at room temperature and allowed to precipitate. The unreacted agents were removed from the precipitate by washing with the distilled water several times. The obtained precipitate washed and dried at 70 degrees Celsius for 25 hours using hot air oven. The obtained product was calcined at 700 degrees Celsius for 3 hours in a muffled furnace to get in crystalline form, then grinded in using an agate mortar to obtain in the powdered form. And it is termed as TB0. For the preparation of doped sample TB5, lanthanum nitrate and terbium nitrate together taken as 0.1 molar solution, and the same synthesis procedure is followed. The XRD pattern of the pristine as well as terbium doped sample is shown here. The standard pattern is also given for comparison. The observed peak positions of the pure sample TB0 was well matched with the standard pattern JCPDS card number 82/2068. And it has scheelite monoclinic phase with the C2/C space group. And the diffraction pattern of the doped sample was also well matched with the monoclinic phase. No additional peaks corresponding to terbium or any other impurities were observed. But, next slide. But the main peak positions of the doped sample is slightly shifted towards the higher diffraction angles due to the incorporation of the terbium ions into the lattice. Correspondingly, a small decrease in the terbium a small decrease in the interplanar spacing values are observed in the terbium sample, and it is tabulated in the given table. The average crystallite size and calculated by the well-known Debye-Schreier equation. And for TB0, it is 12.722, and for TB5, it is 14.792. The average crystallized size of the terbium sample was found to be increased. So the lattice parameters of the samples were calculated using despacing equation. The lattice parameters and the average crystallized size of the samples are presented in the table. Standard values as per the JCPDS file is also given for comparison. A slight change in the lattice parameters value is noted due to the incorporation of terbium ion. Then these are the EDAX spectra of the prepared samples. It reveals the elemental composition of the synthesized sample TB0 and TB5. The EDAX spectrum of terbium-0 confirms the presence of lanthanum, tungsten, and oxygen. Next slide, please. No other elemental peaks are seen in the spectrum, which indicates the purity of the prepared sample, whereas the peaks of terbium ions could be seen in the EDAX spectrum of the doped sample, providing a confirmation for the terbium doping. Surface morphology of samples were analyzed using scanning electron microscopic images shown here. Differently shaped particles are seen in the images, and agglomeration of particles are also evident from these images. So the incorporation of terbium ions may promote the particle aggregation and the growth of irregular crystalline grains. So we can say that doped sample exhibit more irregular shape and size as compared to the pure sample. Next. Then move on to the optical studies. Firstly, UV visible absorption spectroscopy. The UV visible absorption spectra of pure and doped samples were taken to study the effect of terbium doping on the optical property of lanthanum tungstate nanoparticles. That is shown here. Both the sample exhibit a broad band around 240 to 260 nanometer range, which corresponds to the oxygen to tungsten charge transfer transition in WO4 2-. Another band around 320 nanometers observed in the doped sample corresponds to the transition in terbium ions. And the absorption edge of the doped sample is slightly shifted towards the higher wavelength region, which attributed to the photoexcitation from valence band to the conduction band, and also the creation of defect structure due to the terbium ions occupy lanthanum tungstate matrix. The optical band gap value of the samples are calculated using dot plot. The calculated band gap values are given in the table for TB0. Next slide. For TB0, it is 4.13 electron volt, and for terbium-5, it is 3.06 electron volt. So the incorporation of terbium ions in the lattice may cause more structural disorder and distortion, which is evident from XRD result too. And due to the presence of these distortion and disorders, band gap value reduces. Then next is photoluminescence studies. The PL spectra of both the samples were shown here. The PL spectra of the PL spectra of terbium-0 is shown in black line, and the terbium-5 is in red color. And the PL intensity of terbium-0 is very less as compared to the terbium-5. So in order to make a more understanding about the nature of spectrum of terbium-0, it is enlarged and shown in inset. PL spectra of pure sample show a broad feature with a maximal value at 441 nanometer, which corresponds to oxygen to tungsten charge transfer transition within the WO4 2- group. And the doped sample spectrum has 4 strong emission lines, which are attributed to the transition from the D54 level of the terbium ion. The 4 emission peaks of terbium ions are observed at, next line, please. The terbium ions are observed at 496, 545, 587, and 622 nanometer, corresponds to D54 to FJ7 transitions respectively. Next, please. The emission peak intensity of and the peak positions are peak position and also the color region are given in the table. Here the emission peak intensity of the green peak at 545 nanometer is about 5-fold that of blue or red. So the terbium ions are used as green emitters in the doped substances. Next, ma'am. CI chromaticity diagram. CI is a standard color matching reference which helps numerically to identify a color. Chromaticity of a color is specified by the chromaticity coordinates X and Y, which is calculated from PL data. And the calculated chromaticity coordinates are shown in the table and are pictorially indicated in the CIE index diagram. And the terbium 0 sample shows a greenish blue emission, and the terbium 5 shows a yellowish green emission. Due to the incorporation of terbium ions into the lattice, the color of emission changed from blue to green region. Next. In the table, the XY coordinates are shown, and we can say that the color tuning is possible by adding the proper concentration of doping ions into the host lattice. Next, ma'am. Then here are the conclusion of my study. About the structural studies, the XRD patterns revealed that all structural peaks are well matched with the scheelite type of monoclinic lanthanum tungstate. Due to terbium inclusion, main peak position slightly shifted to the higher diffraction angle values. Both the samples exhibited irregular size and shape. The presence of terbium ions promote the particle aggregation and growth of more irregular crystalline grains, which is evident from some images. IDAX spectra confirm the elemental composition and purity of the sample. And about optical studies, from UV visible absorption studies, it is clear that both the sample have absorption band in 240 to 260 nanometer range corresponds to oxygen to tungsten charge transfer. And the doped sample exhibit a band around 320 nanometer corresponds to the transition in terbium ions. And the incorporation of terbium ions cause more structural disorder, which reduces the band gap value. The doped sample has 4 PL intense emission lines, which are attributed to the transition from D54 level 2 of the terbium ions. And the strongest emission spectra of terbium is at 545 nanometer. Due to the presence of terbium ions into the lattice, the color of emission of sample changed from blue to the green region. So the terbium ions can be used as a perfect green emitter in the doped substance, and the terbium doped lanthanum tungsten nanoparticle synthesizer is suitable for UV light excited LED application.
Thank you. It's a nice work. Congratulations. So what is the significance of this photoluminescent studies? What is the significance of this photoluminescent property?
Photoluminescent property, actually, lanthanum tungstate is known as a best host material in the tungstate family for the PL emission. So many literature reports are already there for the europium doping, dysprosium doping studies. So by the proper loading amount, we can observe more intense emission peaks. Basically, tungstate gave a broad emission band. Suppose we can change the emission color by using these rare ions doping into the host material lanthanum tungstate.
Okay. One technical question: how are you getting these chromaticity diagrams? So you make the fluorescence measurements and then plot it, or what?
Yes, sir. Basically, chromaticity diagram, there's a software among with us, and we first of all we calculate.
Data your input? What is your data of input?
Data input is obtained from the PL data, and first of all calculate the X and Y chromaticity coordinates from these data.
Okay. Okay. Thank you. Thank you. Thank you,
sir. Thank you, sir.
Okay, we can go for the next.
Thank you, Soumya. Next presenter, ID number 095, Hisna PA, Department of Physics, University of Calicut, presenting on the topic, the enhanced output voltage of T-dye adsorbed cellulose-based triboelectric nano generator, a novel energy technology.
Is that audible?
Yeah.
Yes.
Okay. I'm Hisna Pierre, research scholar at the Department of Physics, University of Calicut, doing research under the guidance of Dr. P.P. Prathibnan, Senior Professor, Department of Physics, University of Calicut. And the presentation entitled is the enhanced output voltage of T-di-adsorbed cellulose-based triboelectric nano generator, a novel energy technology. The outline of my presentation includes introduction, experiment, result and analysis, conclusion, and references. We know that we are using many small electronic devices. For that small electronic devices, to power up such devices, we need batteries. But the periodical replacement of batteries and disposal and the material used for the fabrication of batteries are highly hazardous to human life as well as the environment. So we need a solution for that. If we can scavenge the unutilized waste energies from the environment to useful electrical energy, it would be a great solution for the usage of for power up the small electronic devices. For that, we are using nano generator. In nano generator, mechanical or thermal energies are converted into useful electrical energy. There are three types of nano generator. One is pyroelectric nano generator, piezoelectric nano generator, and triboelectric nano generator. In pyroelectric nano generator, waste thermal energy is converted into useful electrical energy. In piezoelectric nano generator and triboelectric nano generator, mainly mechanical, low frequency mechanical energy from the environment is converted into useful electrical energy. Now I am concentrating on the triboelectric nano generator, which is invented by Zhong Lin Wang in 2012, which is based on the coupled effect of triboelectrification and electrostatic induction. Triboelectrification, tribo, it's a Greek word which means friction or contact. When two dissimilar material come into contact or come into friction, there would be a generation of charges. That charges is called tribo charges. And as we know, electrostatic induction, when an charged body come near to the uncharged body get induced some charges. That is called electrostatic induction. Both these triboelectrification and electrostatic induction are nothing but our everyday static electricity. Why we need tanks? Because it converts waste unutilized mechanical energy like human motion, wind energy, even our breeze can be converted into useful electrical energy, which is an eco-friendly and it have high efficiency at low frequency, which is low cost, portable and lightweight. Moreover, they have multiple mode of working mode and diverse stores of materials. And I said that there is a diverse choice of materials, so we have to rank such all the materials in order to gain or lose electrons as a series. That series called triboelectric series. In the series, the above materials are called tribopositive materials because it have the tendency to donate electron, and the bottom materials is called tribonegative materials, which have the ability to gain electrons. In my work, I used paper, cellulose paper as the tribopositive material and polypropylene as the tribonegative material. And I said that there are different modes of operation. There are four fundamental modes of operation. One is contact separation, relative sliding, single electrode, and freestanding mode. Here the green and blue are the triboelectric materials. When these two triboelectric materials come into contact, the tribonegative material become negatively charged and tribopositive material become positively charged. When these are come in contact, the respective tribo charges will generate, and as they separated, respective opposite
charges will be induced on the electrodes. These yellow ones are the electrodes placed on the above and below the triboelectric materials. And due to the disturbance in the electrostatic potential and the electron distribution, the output current will be flow through the outer circuits. This is the main principle behind all these four fundamental modes of operation. In my research work, I have used this freestanding mode of vibration. Next is experiment. The materials I used are the T-dye adsorbed bond paper, polypropylene sheet, and aluminum foil. Why I used bond paper? This is a cellulose paper. Bond paper is a biodegradable, rich in cellulose content, good absorption ability, and thicker. Since it is thicker, it can withstand many mechanical excitation. And since it contains cellulose contents, it acts as a tribopositive material. To enhance the tribopositivity of the bond paper, cellulose paper, I coated the T dye on this cellulose paper since it contains phenolic hydroxyl group, carboxyl group, and amino groups. These functional groups enhances the tribopositivity of the cellulose paper. As a tribonegative material, I used polypropylene sheet, which contains methyl groups. This methyl group have the tendency to withdraw electrons as compared to the cellulose paper. As an electrode, I used aluminum foil since it is easily available and cost effective. From the materials chosen for the experiment, we can conclude that it is a simple, cost effective, and easily manufacturing triboelectric nano generator. Next is working of triboelectric nano generator. This yellow one is the polypropylene sheet. Beneath this polypropylene sheet, I pasted the aluminum electrode, and above this T-dye adsorbed cellulose paper is slided over this polypropylene sheet when I apply tangential force manually. And this T-dye adsorbed cellulose paper act as the freestanding triboelectric layer. As it moves from left to right or right to left side, there would be an disturbances in the electronic distribution in the electrodes, aluminum electrodes. As a result, the output voltage flows through the outer circuit. As a result, we get alternating output. The result of this triboelectric nano generator is measured using DSO. For a bare cellulose paper, the voltage obtained, the output peak-to-peak voltage obtained is almost approximately 3 volt. Whereas when I used the T-dye adsorbed cellulose paper as a tribopositive layer against the tribonegative polypropylene sheet, I got the output peak-to-peak voltage almost approximately 6 volt. So there is an enhancement in the output voltage 2 times. Next is from the introduction, I said that we can use it for small electronic devices. So I experimented it for the load performance of the two LEDs. For self-powering of LEDs, the output from the tank is connected to bridge rectified in order to rectify the alternating current, alternating output voltage, and then it is directly given to seriously connected 12 LEDs. The output when I applied the mechanical force on the triboelectric nano generator, electrical output is generated. That electrical output is driven these 12 LEDs, and this photograph shows the 12 white LEDs driven by this nano generator. And next is characteristic of commercial capacitor. The output from the triboelectric nano generator can be stored in the capacitor for the further usage. When I used the cellulose paper as bare cellulose paper as the tribopositive material, within the 70 seconds, I got only less than 1 voltage storage. And when I used T-dye adsorbed cellulose paper, within 70 seconds, I reached to 2 voltage of of electrical energy. And as the capacitance value increases, the time taken for the storage also increases. Next is the conclusion. I explained the triboelectric nano generator and its advantages over other nano generator. From the material used and the fabrication method, we can conclude that the fabricated triboelectric nano generator is simple, low cost and eco-friendly one, and which can be fabricated by easy method. The low output load performance of the triboelectric nano generator is done by using 12 commercial LEDs, which can be the tank can be driven 12 commercial white LEDs, and it can be charged 1 microfarad capacitor in 70 seconds to 2 volt. This is references, and thank you, sir.
Thank you. It was a novel type of work, and congrats.
Thank you, sir.
Towards the end, so is it just do you think that this will have a commercial application towards the end?
Yes.
What?
Yes, sir. Yes, sir. It should have. There are so many purposes related to triboelectric nano generator, and they are used for the small electronic devices. And not only in the for small electronic cases, they are using as sensor also.
So, what are the other materials used so far for making these triboelectric nano generators already?
My material, I chosen the T dye. It is a
No. Yours I understood, but what are the other materials which are used?
In the triboelectric series, we have so many materials. We can choose any of any tribopolarized, oppositely tribopolarized material for this triboelectric nano generator.
Such reports are available?
Yeah. Of course, sir.
Then,
but my material is novel one. So far, no one is introduced as such T-dye adsorbed triboelectric nano generator.
okay, how did you maintain the mechanical energy?
Now I used the, since I need to sense the human mechanical force, I used the mechanical energy by me itself.
Okay. Okay, thank you.
Okay, thank you. Thank you, sir.
Thank you, Hisna.
Thank you, ma'am.
So finally, we come across last presentation.
We are moving on to the last presenter of this section.
Yeah.
ID number 04 Vishak V. Mohan, Department of Physics, University of Kerala. He is presenting on the topic Lab to Land Approach Supercapacitors.
Ma'am, is it visible?
Yes.
Okay, fine. Good evening, all. Myself, Vishak V. Mohan, PhD Research Scholar, Department of Physics, University of Kerala, Karyavattam, Trivandrum. This is our latest research work regarding lab-to-land approach in sort of supercapacitors under the guidance of Dr. Ragi RB, Principal Scientist, CSIR, NIST, Trivandrum, and Dr. Manuraj Mohan. He is our co-author. He is from Kerala Technology, Bangalore, Karnataka. So these are the main contents. So why we are using supercapacitor? Actually, we have batteries. Then why we are moving to supercapacitor? Batteries have high energy density and a wide potential window. But the main drawbacks of batteries are its cost, high weight, lifespan is comparatively low, safe operation is not possible, charge speed is comparatively low, and materials are highly costly and not at all eco-friendly. In the case of supercapacitors, the main drawbacks are energy density and a potential window. So in this work, we have try to increase the energy density and the potential window by using commercial mass loading of electrode material, by introducing the commercial mass loading of electrode material. And other positive things are its lightweight, cost is comparatively low, lifespan is high, safe operation is possible, power density is much very high. This is the main advantage of supercapacitor over batteries. That is, charge speed is comparatively high, and a wide variety of materials are possible for the fabrication of supercapacitors. So By coming to aim, to improve the energy and power density of supercapacitor, commercial level mass loading of 2D materials for practical application through vacuum-free deposition techniques to design devices with a wide potential window and having high stability. So we know that supercapacitors are widely used in transportation systems. Supercapacitors are used in startup mechanism for automobiles. Due to its very fast charging and discharging properties, supercapacitors make a great tool for regenerating braking vehicles. They are used in electric vehicles to extend the life of batteries. Actually, this technology was adopted by Tesla and Toyota in their latest model cars. And the supercapacitor provide both power in stop, go and go vehicles, example buses and trains. Supercapacitor used to power emergency systems in aircraft that we already know. So working of a supercapacitor consists of two electrodes and a porous separator and an electrolyte. Up to by knowing its mechanism can be divided into two double layer capacitance and pseudo capacitors, and a combination is called hybrid capacitance. Hybrid capacitor. The main equation for calculated specific capacitance is shown here: 2I by m into delta V by delta T. I is the current and delta V by delta T is the scan rate by potential, and m is the mass loading. Here we can see that m is in denominator, because that's why when we are increasing the mass loading, the capacitance will decrease. From this equation, we know that if we are trying to increase the mass loading, the capacitance will decrease. But for commercial application, the mass loading should be high. So in this work, we are trying to maximize the mass loading and maintaining the capacitance. So the material we chosen is 2TWS2 because it has higher theoretical capacitance and high surface area, and it is an analog of graphene, and a 2D electron-electron correlation among W atoms, which can enhance the planar electric transport. So these are the materials used for the synthesis of WS2, and a hydrothermal method was adopted for the commercial mass loading of 2D WS2. This is the schematic picture. So by coming to resultant discussion, figure A shows the XRD, B shows the Raman, C shows the band gap analysis, and D shows the FTR. And XRD external phase of WS2 are confirmed, and Raman analysis shows that two major peaks confirm the in-plane and out-of-plane vibration of WS2. And the band gap shows an 1.72 EV, which ensure the presence of few layers of WS2. And the BET surface analysis shows that the material having a highest surface area of 28 meters square by gram. By coming to FSM analysis, A and B shows a novel flower-like morphology, and C shows the EDAX spectrum, where W and S presence of W and S were confirmed. No other impurity phases were observed. And by coming to D, it shows the TEM images, a nanosheet-like morphology was confirmed from TEM analysis. So by coming to electrochemical analysis, first we are for a lab scale, we have used KOH and electrolyte, and check the A shows the CEV and C shows the GCD. These are the two parameters that depends upon the capacitance and the behavior of the supercapacitor. The CV shows that a quasi-rectangular shape, which results the pseudo-capacity property of the material, and the GCD also a nonlinear behavior shows from the rectangular shape. From the triangle shape, that's also ensure the presence of a pseudo-capacity behavior. The capacitance was calculated, which is around 205 farad per gram at 5 milliwatt per second over the mass loading of 30 mg per centimeter square. So by coming to impedance analysis, the solution resistance is only 0.7 ohm, and charge transfer resistance is less than 1. That means 0.28 ohm, which shows the better conductivity of the material, and the device shows an excellent power density of 0.8 kilowatt per gram and energy density of 14 watt hour per gram. And over that large 10,000 cycle, it shows 100% stability. The percentage contribution is showing both the presence of EDLC and pseudo capacity. So this is the literature among WS2. We have reported the highest specific capacitance of WS2 over higher mass loading. And this is for commercial application. We have chosen an organic electrolyte. And here I have gone from 0.8 volt to 1.5 volt potential window. There is no much difference in peaks in both in shapes and the characteristics that ensure the stability of the material. And the impedance spectroscopy also shows the RS value is 3.4 ohm and RCT value is only 1.2 ohm, and the capacitance has reduced to 168 farad per gram. Actually, this is the highest reporting value of WS2 material in organic electrolytes, not only in WS2 compared to other materials also. This is the highest reported value in 30 mg high mass loading condition. So by checking with the previous commercially mass loaded devices, we are on the top. So application, just 1 second charging, a single LED will leads up to 10 minutes and with a 45-second charging, 8 LED will continuously leads power up to 5 minutes. So this is a single LED, just 1 second charging. The single LED will leads up to 10 minutes. This is the time showing. And we have fabricated, we have designed a toy car using this supercapacitor. I will try to play the video. So with the collaboration with Startup Mission, we are trying to fabricate supercapacitor for IoT-enabled application for rural areas. And these are the summary and conclusion. Pure phasor WS2 nanoflow-like morphology of synthesis were one-step vacuum-free technique. Fabricated commercial level mass loading of 2D WS2 electrode material. This is first time reporting. Offers a high specific capacity of 205 farad per gram at 5 milliwatt per second, which is greater than previously reported WS2 based device. And also in organic electrolytes, we have reached 168 farad per gram at 1 ampere per gram current density, which is also first time reporting. Both devices shows 100% stability over large cycle, that is 10,000 charge discharge cycle. This is our team and this is the teamwork. So the friends, acknowledgement, thanks for STAM23 and their coordinators and all support from the different universities from India and abroad India and the government of Kerala and the government of India. Special thanks to CMET, ICER and the CSI and NIST. Thank you.
Thank you. It's a nice presentation, nice work. Congrats.
Thank you, sir. Actually, this is we are going for a patent. That's why some logos are over the pictures. CSI and
Okay, okay. It's okay. Okay, how many are working with you?
Actually, we are 4 members working in supercapacitor, and 2 of them are working in batteries, and one is working in latest air electrode batteries.
Okay.
And also sensors and photocatalysis is also started.
Anyway, nice work. Congratulations.
Thank you, sir. Thank you.
Most of our presentations as well as the work were good. Also, I thank MA College for giving me an opportunity to evaluate the work presented by the research scholars of various organizations. Thank you very much.
Thank you.
From my side too, thank you for inviting me to evaluate the sessions, and most of the presentations were really informative and real good efforts from the young future scientists. Congratulations to all. Thank you.
Thank you. So we have reached the end of this section. On behalf of STAM and MA College, I extend my sincere thanks to Professor Dr. Thomas Varghese, Newman College, Tiruvira, and Professor Dr. Franklin J, SH College, Sevara. And also, I would like to thank all the participants here. Thank you.
Okay, thank you.